Good evening, sir.
Hi, Anna.
Hello, everyone. Welcome to this session. We have Professor Arun Rajkumar with us, who has kindly agreed to join this session and take up the queries that you have so far in the ML Foundations course content. So you may probably raise your hands one by one, and sir will be taking your queries one after the other. So please raise your hands if you have any questions. Over to you, sir.
Yeah, so if you can give me a minute, I'll just log in from my tablet as well, so that.
Sure.
Okay, I think I've joined via the tablet as well. Let me share my screen there. Okay, so can you, Anamika, if you can enable screen sharing?
Okay, sir. Give me a moment.
Yeah.
Sir, which is the ID that you're using in your tablet?
Oh, I think this should be Chandrasekhar. Yeah.
Okay. Okay.
That is what I'm logging into. Yeah. Okay. Good. Okay, great. Welcome everyone. So this is kind of a, not. I mean, this was planned recently, but I see some other session that's perhaps happening now. So feel free to attend the other session as well. There is a YouTube recording for this session. You can come back to this later on. So if you had any questions, you can always use the Excel sheet to add those questions for people who want to attend the other session. And I'll try to answer them here as well so that you can come back to this later. Okay, so let me first try to understand the overall questions that people might have, and then I'll probably kind of try to answer some of them together. I think that would be better. So if people have general questions, let me hear about them, and then we can start. Yeah, Pranav, go ahead.
Yeah, hi sir. Good evening. So sir, my question was about eigenvalues and eigenvectors. Like it is very hard for me to understand. First of all, I'm not from technical background. So it has been very hard for me to understand what context or what role do they play in actual machine learning and AI.
Okay, so eigenvalues, eigenvectors, we'll talk about that definitely. Yeah, so more questions. Yes, Samit, please go ahead.
Yeah, sir. Am I audible?
Yes.
Yeah, sir. One question that I have regarding the projection matrix. Suppose any matrix, when we are taking the linear transformation, basically it will changes the basis vector. So if with the standard basis vector, if I 1 0 0 1, I have some vector in that plane. Now, when a linear transformation is take place, basically that basis vector will get changed as per the matrix coordinates. Say 1 2 2 3 is the transformation matrix. So the corresponding shifting of that vector from 0 1 1 0 to that 1 2 2 3, where it will stand. In that way, all the linear transformation is take place. That's what I understood. Now, my specific question is, when I'm taking any projection. Projection means if there is a vector in, say, in 2 dimension or 3 dimension, I'm taking the shadow into the perpendicular drop into the corresponding that plane, and that is the projection of that vector in that plane. But how this projection matrix is means changing that to that plane, I am not able to properly visualize that thing. I can understand a little bit, but not able to very clear in that.
Okay, sure. So projection is another thing we'll try to cover today. Yeah. Pritodeep, you want to go next?
Yeah, good evening, sir. Am I audible?
Yeah, you are. Hi.
Yeah, hi. Sir, I just wanted to, I also pointed this out in the Excel sheet. I'm having trouble with multivariate calculus. Specifically, the concepts of univariate calculus, I more or less understand, but I am unable to apply it to higher dimensions or like more than one function. So visualization is one key aspect where I'm facing issues. And I also, honestly, I also skipped this in maths too. So here again, I'm facing a big issue. If some basic concepts of multivariate calculus can be discussed, I'll be very grateful.
Okay. So we'll see if we can fit that as well. Okay. Anything else that people had at a high level or? Okay, good. So what I thought I'll do is I'll kind of do a very basic high level, give an intro for some time about, these linear transformations and subspaces and things like that. So are those things clear to everybody? The, 4 fundamental subspaces and what happens and so on. Is that clear to everybody? Because I also saw some of you had mentioned in the Excel sheet about that as well.
Regarding the 4 fundamental subspaces, the 2 subspaces, that is null space and the column space, it's more or less more clear, because there I can see a lot of application where it is going, how it is related. But when I'm coming to the row space and left null space, this thing I'm not able to at all visualize where this my vector is going on, in where I am total lost. It is there, but I am not able to visualize like the way I can see the thing in null space and the column space.
Okay, so maybe that's a good place to start. Some of you might understand this better, but then, to understand later on projections and least squares and even eigenvalues and eigenvectors, right? So somehow we need to, basically understand what are matrices, what are linear transformations, and why do we care about these subspaces in the first place, right? What I'll do is I'll basically give a very high level introduction, take 5 minutes. This is not, I'm not trying to replace the classes. Use this as kind of a, revision or some kind of doubt clearing session. I cannot do the whole thing. My goal is to give you some intuition as to what these things are and what these objects are and why they may be relevant in the first place, right? So with that understanding, we'll get started. So basically, whole of, in some sense, linear algebra is to understand, the idea of linearity and how it maps something geometric, that intuition that we have in 3-dimensional space, how you can, transport it to higher dimensional spaces. In some sense, that's the idea. What is linear? In linear algebra, right? So basically, you want to understand some kind of functions from some space. Okay, so let's see if this works. Some space to some other space, right? So there is some transformation that starts from one space and then takes vectors from one space to another space. Now, basically, you are mapping elements of one set to another set. This is set 1, and then this is set 2. There are 100 ways you can map from set 1 to set 2. Now, when set 1 has very nice structure, and this mapping also has some nice structure, then a lot of interesting, structural properties emerge. Right, so that is what study of these structural properties is, in some sense, the high-level idea of linear algebra itself. So now, what property do we assume about set 1 is that we just assume 2 properties. One is that, Okay, so what is this set 1 that I'm talking about? This is just a bunch of vectors, let's say, right? So this is a set of vectors. But then this is not an arbitrary set of vectors. This set of vectors have to satisfy just 2 properties, right? So we want to say that if, let's call this set V, and then if some vector A is in this set V, we also put some scaling of this vector also in V. This just means pictorially that, if I pick some vector, and then if this point is in my set, then all possible scalings of this point are also in my set. Right, so if that point is there, the whole line is there in 2-dimensional. That's what it means to say that you're putting all scalar combinations of this, scalar multiples of this vector into the set. The other thing is that if you have 2 vectors A and B in the set, then their sum is also in this set. Right, so for example, if I take 2 vectors, this is one vector, this is one vector, which means I can add these things up, and then the sum of this vector will also be there in the set. Maybe if I put this vector also, then the moment I put this vector, I know all scalar multiples have to be in the set. And not only that, I can pick any 2 vectors, maybe this, which means that I have to add the sum of these 2, which means this point will also be there. So the vector sums happens as, this is vector u, this is vector v. Then if you add vectors, then you have to put the vector v on top of vector u, right? So, and then you add them up and draw the line from the origin, right? So this will also be there in my set. The moment this is there, the whole line will be there, right? So now you can imagine if I keep putting these vectors, I get a set of vectors with this nice property that these 2 properties hold. Any vector I take, the scalar multiple is there. I take any 2 vectors, their sum is also there. Right, so I start with such a set, which has a name, which is called as a vector space, and now I apply some function to this set to get another set. Right, so on this function maps from one vector space to another vector space, and this function is not any arbitrary function. We are asking for linear functions basically. What does linear function mean? Linear function simply means that, well, that function should satisfy simple property that the function applied to the sum of 2 vectors should be the sum of the function applied to the vectors, and the function applied to some multiple of vector should be the multiple of the function applied to the vector. Right, so basically this is what is meant by linear function. Right, so if I change the input, if I multiply the input by 2, the output also should get multiplied by 2. If I add 2 things and then apply the function, it should be same as if I applied the function and then added them. Right, so if I ask for these 2 properties for this function to be satisfied, then you can ask what are the functions that satisfy these, and then it turns out that any function that satisfies this can simply be represented using our well-known matrices. Right, so which means that if I take some x in this vector space, this transformation itself can be represented using a matrix A, and then out comes AX, right? So this will be in the another vector space. So this is the idea, the simple idea, starting with you want to understand functions from sets to sets, but then these are not arbitrary functions. These are functions which satisfy these 2 simple properties, which are called as linear properties. And once you put this constraint, then all such functions can be represented using matrices, right? So this is the basic idea. And so we want to understand these linear functions. It is important to understand matrices themselves. Now, matrices come in different forms. So, why do we care about matrices? Why do we care about, understanding these functions? That's because, in a lot of practical applications, you would have to solve equations of the form AX equals B, right? So, well, for example, think of, let's say a simple example is, a kind of somehow I'm just making this example up, not necessarily a real world application. Nevertheless, let's say I make this example up. Let's say you go to a store and then you buy 10 kgs of sugar, 5 kgs of salt, and 3 kgs of something else, rice maybe, and then you are charged a certain amount, right? So the next day somebody else goes and they buy 5 kgs of something, 10 kgs of salt, and then maybe 7 kgs of sugar. They are charged something else, right? So now you can think of your, maybe 5 kgs of sugar, 3 kgs of salt, and 4 kgs of whatever rice. And I had to pay $100. Maybe 6, 5, 3 was $200. 5 to 4 was $150, right? So maybe I have this data. And now I want to understand, well, what is the cost of 1 kg of sugar, 1 kg of salt, and 1 kg of rice, right? So I want to know the cost of each of these, right? So maybe this is sugar, maybe this is salt, maybe this is rice. I don't know, right? So I don't, if I'm only told these price and I'm told how much did I buy, if I have to, calculate the price of each sugar, salt, and rice, now you can think of that as sugar is X, X1, salt is X2, rice is X3, then essentially you are solving AX equals B, right? So where A is the matrix 5, 3, 4, this is 6, 5, 3, this is 5, 2, 4, right? Sugar price, salt price, rice equals 100, 200, 150, right? So these are our simultaneous set of equations that you want to solve. And this is just an example of, I just cooked up this example, but then these kind of examples, appear all over the place in engineering, right? So which means we want to understand, when can you solve this problem, which is why we want to really understand, matrices themselves, right? So once you understand matrices themselves, then you can answer when can you solve this problem. Then the question is, how do you solve this problem? Where is the solution? All those things come later. Okay, so there is a question in the chat box which says, what is the definition of linear combination and how can we distinguish between linear combination and non-linear combination? Well, whatever I said is essentially a linear combination so far, right? So you have, let's say a vector, 1, 2, 3, and a vector 4, 5, 6. Let's say these are two vectors. Now, a vector is said to be a linear combination of these two vectors if, I can multiply this with some scalar C1, multiply this with some scalar C2, and then add them up, right? So maybe C1 was 2, C2 is 4, which means I'll get something like, I think 18, 22, 24, 6, 30. Right, so which means now you say 18, 22, 30 is said to be a linear combination of 1, 2, 3, and 4, 5, 6. Right, so you are linearly combining. Why is it linearly combining? Because if I double these coefficients, the output also doubles. Right, so instead of 2, if I make it 4 and 8, now the output would be 2 times this. Right, so it doubles. That's why it's linear. Linear means line. Right, so how much ever you increase in the x-axis, the y-axis also increases proportionately, right? So that's why it's called a linear combination. I hope that is clear. Okay, so now what I've kind of said so far is that we kind of want to understand, matrices because we want to solve linear equations. That is one, you might, if you are coming from an engineering point of view, maybe that is one reason from where you want to come up. Okay, so there's one more question, I'll answer that. What is a non-linear combination? Well, anything that is not this is a non-linear combination, right? So anything that is not a linear combination is a non-linear combination, right? So if you cannot get a vector using a linear combination, well, okay. So give an example. For instance, I might say that, let's say 1, 1, 2, 3, right? Maybe I'll say 5 times 1, 1 plus 6 times 2, 3 plus 1, 1 dot 1 in. So element wise product, let's say, right? So maybe this is a non-linear combination. Is a polynomial equation a non-linear combination? Yes. So polynomial with degree 1 is a linear combination, but then if you have higher degree polynomials, that might be a non-linear combination. A plus alpha b into b. What does that mean, Lee? What do you mean by A plus alpha b into b?
So I was just saying that could be a non-linear combination.
Okay, so I think we have to be clear about what we are combining, right? So unless we are clear about what we are combining, we won't understand what is the definition. So when you talk about linear combination, you're just talking about linearly combining a set of vectors, right? So you have a bunch of vectors, and then the only operations you are allowed is you can scale these vectors and then add these vectors. Any vector that can be got by scaling and adding these vectors is said to be a linear combination. If you do any other operation, right? So if you multiply, maybe element wise, if you square the entries of the vector, all these things are non-linear combinations, right? So maybe 1 cube, 2 square, 3 square, right? So these kind of weird functions are all non-linear combinations, right? So yeah, question?
No, so as I said, I understood that when explained right now.
Sorry, say that again.
Yeah, I just said that. Thank you. I got it.
Okay, you understood that. Great. Okay.
So
okay.
one thing, sir. Sir, you told that anything apart from scaling and editing is a non-linear.
It's not a linear combination. Yes.
Not a linear combination.
Yeah.
So in our line equation, ax plus by plus c equal to 0. That's a linear equation. So if we are going apart from this matrix, this linear algebra concept, if we are going, it's how do we know that this is a linear equation?
Yeah. This is a linear equation of x and y.
Right? X and y. So ax square plus by square plus c will be a nonlinear equation. You are saying like that?
That is correct, right? So basically, you have to think of it this way, right? So I am giving you a vector x, y, and then I'm mapping it to a times x plus b times y, right? So this x itself, now this is how I will think about this, right? So, for the moment, let's say this is x times 1, 0. Maybe let me do it this way, right? So it depends on how you are thinking of the input, right? So if you're thinking of the input as x, y, and then the output is ax plus by plus c, well, technically this is what is called as an affine function because you have this extra c as well. But you can think of this as if this is this comes from a matrix, right? So you can think of this as if you have a matrix AB and you have a vector xy. Now, if I do the dot product of this, that is ax plus by essentially. But then if you want this extra c, then typically you assume that there is an extra dimension that you have here, which is 1, and then you do a, b, c. Now this is ax plus by plus c. Right? So this would be a linear function in a one extra dimensional space, right? So that's why this is linear, because this can be expressed as the output can be expressed as a matrix times the input. In this case, the matrix happens to be just a vector, right? So ABC.
Focus.
The input is just x. Let's not confuse too much about this, right? So let's just think of these as so maybe I should start looking at these 4 fundamental subspaces. Then I think things will perhaps become much more clearer. What I'll do is I'll kind of share here in this screen. something that I had prepared. Let's see if that works. Right. Well, let me know if you're able to see the screen. You are, right? Okay. Okay. So
Visible.
yeah, thanks. Let's start with the simple matrix, right? So we know that matrices represent linear transformations. We'll start with the simple matrix A. And now what does this matrix do, right? So as a function, it's mapping something to something, right? So what is it mapping, right? So what is the input to this matrix and what would be the output to this matrix? Can somebody tell that? Well, what are the valid inputs to this matrix and where would the valid outputs be? In what dimension?
Inputs.
Yeah.
Inputs can be some point as a vector.
Yeah, in what dimension?
Is another.
R3.
Yes.
R3 will be input and output will be R2.
Very good. R3 will be input and output will be R2. So yeah. So the input is going to be in some three-dimensional vector, and then you apply this matrix, and the role of the matrix is to map this three-dimensional space to a two-dimensional space, right? So for any three-dimensional point, it is going to give you an output in two-dimensional space. Why? Because this is a 2 cross 3 matrix. So which means the three-dimensional vector is 3 cross 1. So if you multiply 2 cross 3 with the 3 cross 1, you are going to get a 2 cross 1, right? So the output is going to be in two dimensions. Is this clear to everybody? I hope this is clear. Right? Okay.
Yes, sir.
Now,
excuse me, sir. Can I repeat again, sir?
So what I'm saying is your input should be in 3-dimension, and then you apply your matrix A, right? So 3-dimensional vector is a 3 cross 1 vector, right? Now A is a 2 cross 3 matrix, right? So we know matrix multiplication can happen only if the columns of the first matrix and the rows of the second matrix have to match, right? So now your input is a 3 cross 1 matrix. It's a vector, but then you can think of it as a 3 cross 1 matrix. Your A is a matrix which is 2 cross 3. So 2 cross 3 and 3 cross 1 will match, and the output will be 2 cross 1, right? So A cross B and B cross C will give A cross C. So it takes any three-dimensional vector, gets mapped to a two-dimensional vector. Is that clear?
Yes, sir. Yes, sir. Clear.
Okay. So now the question is, this doesn't tell us too much about the matrix itself, right? So it's just saying it's mapping three-dimensional to two-dimension. But then we need to understand more about this matrix. Why? Because we want to solve linear equations using this matrix later on, right? So the fundamental question is, can we say more about this matrix, right? So every matrix which is 2 cross 3 matrix has to map three-dimensional space to two-dimensional space. But then there are some numbers in this matrix, right? So these numbers should somehow tell us something more about what how is it mapping, right? So is it arbitrarily throwing points around? Well, it can't do that, right? So it has to somehow in a structured way map three-dimensional vectors to two-dimensional vectors. So what is the structure that we can get out of this matrix? So that's the question we are trying to ask. And if you want to uncover the structure, where should we look for, right? So that is what we'll start by asking, right? So that's the first question we'll ask. Now, so what I'm going to do is I'm going to randomly pick points in three-dimensional space, right? And then I'm going to apply this matrix. I know it is going to fall in two-dimensional space, and I want to observe where does it fall in the two-dimensional space, right? So I'll pick some random vectors, and then I look at the corresponding vector. For example, this is one vector which is pointing in some direction in three-dimensional space, and then on the right-hand side, what you're seeing is the corresponding two-dimensional vector in the two-dimensional space. This is applied to one particular vector. Now I'm going to do this for several vectors, and then I'll run a animation and let's see what happens, right? So I'm kind of, what you see on the left is two-dimensional, three-dimensional vectors. And now I'm applying A, and what I'm observing on the right is where does A take it in the two-dimensional space, right? Now, what do you observe, right? So immediately you're seeing, well, on the left-hand side, there doesn't seem to be any pattern. I'm just arbitrarily picking vectors everywhere, all around the place. But on the right-hand side, in the two-dimensional space, there seems to be some pattern, right? So I'm sure all of you, I mean, that's the first thing that should have got you right? So now, what is it telling us, right? So it is immediately telling us something more about this matrix, right? So, okay, that's a chat question. Sorry. So it is telling me something more about this matrix, right? So it's telling me that, well, just by saying that the matrix is 2 cross 3, I know that the output is going to be in 2 dimensions. But now this particular matrix A that I wrote down earlier seems to be doing more, right? So it has more structure than just mapping 3-dimensional space to 2-dimensional space, right? So it is mapping to a 2-dimensional space, but then not all over the place, right? So it's only mapping it in a particular line, right? Now, so now if you look at this lines, right? So if the vectors that it ends up being in, right? So after you apply x to A, x can be anywhere in 3-dimensional space. After I do the AX, now I observe that all the vectors are along this line, right? So along the line that x plus y equals 0, or in other words, if I think of that as, I mean, if x plus y equals 0 means that y equals minus x, right? So everything has the property that it is of the form x comma minus x, right? So maybe there is some point which is 5 comma minus 5, maybe some point which is 2 comma minus 2, all sorts of points are there, right? So I can see a spread. Different color means different vectors corresponding. I mean, there are only few colors, so you won't be able to see the exact mapping, but then you get the idea, right? So it's spread all around the place. So why is this happening? Here is the A that we have, right? So this is the A that we had. Why does A do this? Can somebody answer that?
Because in the matrix, although it is having 3, but it is linearly dependent on each other.
Right.
If I can take this 1 minus 1 and can expand the whole set. I need not to be write all these things. That is why it is squeezed down to that single line.
Or the projection is falling on the
Projection?
Depends on column space.
Depends on?
Column space of the matrix.
Yeah. So why is it? No, the question is simple, right? So why are all the vectors after I apply A of the form x comma minus x? Can you look at the matrix and tell me that?
because they are forming projections
all
on the
the-
spaces.
All the
respective
columns are
spaces.
linearly dependent. Like there is only one column that actually matters. All others are scalar multiplication of that column.
Because
Okay.
they are part of the same
One row is
subspace.
Same.
Okay.
Second row is the negative of the first row, minus it.
The second row is
Depend on
first row.
yeah.
Okay.
So basically, what happens is, like, if you take each element of that row vector, they would be like the opposite sign of linear combinations of those individual elements of those row vectors. So if you take the row vector as 1 0 0 plus minus plus 0 minus 1 0 plus 0 0 2. So if that is like if you can deconstruct the row vector of A as that, so each of those elements, right, that 2 cross 1 matrix that you get as the result, that is the product, would basically be like the opposite sign and the linear combinations of each other.
Okay. I kind of got what you're saying. So I think there is some question in the chat. Are we multiplying the input matrix with A, the input with A, right? So what we are multiplying is, so this is X. What you're seeing on the right hand side is AX. Is that clear?
Yes, sir. Yes, sir. It's clear.
We are picking something from R3. We are multiplying the 3 cross 1 vector with a 2 cross 3 matrix. And we are converting it to an output.
Correct.
So we are picking numbers that will give the output that we want. So we are forming a line equation basically. When we multiply, what we get will be equation of the line that we want.
Yeah. So okay. So you are all giving me general results.
They are
yeah.
part of the same subspace.
Okay. So fine. But then that's again a general answer. Okay, so let's see what's happening, right? So what does it mean to say I'm multiplying a 3-dimensional vector with this matrix A, with this specific matrix A, right? So this matrix has 3 columns. Now, let's say my input is 1, 2, 3. Now, the way you should think about multiplying the matrix A with the input 1, 2, 3 is you are linearly combining the columns of the matrix A with the coefficients given by your input. It means that you are taking the first column, which is a 2-dimensional vector, multiplying it by 1, second column multiplying it by 2, third column multiplying it by 3, and then adding them up, right? So that would be your output. Now, in this particular matrix, each column is just a multiple of the other column, right? So if I plotted these 3 columns in R2, right, so they'll all fall in the same line, which means no matter how I scale them and add them up, they are still going to fall on the same line. And that line in this particular case happens to be the line which is x plus y equals 0. Does this make sense?
Yes, sir. Yes, sir.
Yes, sir.
Okay. So, sorry, I'm unable to hear.
Yeah, can you repeat it once? I got lost.
Yeah. So what I'm saying is that, so let's understand the effect of a matrix A on a vector as follows, right? So here I'm taking the vector 1, 2, 3. I'm multiplying A times 1, 2, 3, right? So now you can get the output as follows, right? So you take the first coefficient 1 multiplied by the first column, that would be 1 minus 1. The second coefficient 2 multiplied by the second column, that will be minus 2, 2. Third with 3 with the third column, that will be 6 minus 6. And now these 3 will be 3 vectors. Now, where are these? So one vector is 1 minus 1. The other vector is 2 times minus 1, 1, which is minus 2, 2. And then the third vector is 6 minus 6, right? So all these vectors are actually on this line, right? So 1 minus 1 would be here. Minus 2, 2 would be here. 6 minus 6 would be here, right? So no matter how I scale, I'm going to be here. Now, which means if I sum them up, I'm still going to be here only, right? So I cannot escape this line. Simply because my vectors, initial vectors were all on the same line, right? So now don't look at this as a matrix, just look at this as 3 vectors in R2. Now all 3 vectors are on the same line, which means no matter how linearly I combine them, they are going to end up in the same line. Does it make sense?
Yes.
Okay.
Yes.
Okay, great. So now this is one structure that we are immediately observing about this matrix, right? So which is a good thing to know, because we know something more about this matrix, right? Now here is another picture. Now again, I'm going to pick vectors from R3, and then I'm going to see where they get mapped to A. But this time, I'm not going to randomly pick vectors from R3. I'm going to slightly intelligently pick vectors from R3. But now, how did I pick these vectors, and with what property I have in mind? You will know once you see the animation, right? So now, let's say I again start picking random vectors from R3, and then I apply A, and then I look at the corresponding answer on the other side. Now, what is happening? What is different from this picture from the previous picture?
It's falling on the same point.
It is falling
It's
on the same point.
0, 0,0.
And the point is not an arbitrary point. It's a special point.
Yes.
Right? So the point is actually 0, 0, right?
Yes.
So again, it looks like I'm arbitrarily picking vectors, right? So all over the place on the left-hand side. And then what happens on the right-hand side, though, is that A is mapping all these vectors on the left-hand side to a single point, which is the 0 point, right? So somehow, these vectors have to also contribute to understanding A, right? So because they are in some sense special in that they are kind of annihilated, right? So they don't contribute anything on the right hand side. They map to 0, right? So we'll talk more about these vectors and why they are useful. There are questions on the chat before that. Okay. Yes. So somebody has already observed that this is in fact what you already know as some name. Okay. So yeah. So this was the set of vectors, and all of these map to 0. And now if I actually looked at this closely, this is actually forming a plane on R3, right? So this plane, which all of which gets mapped to the 0 vector, is what you're calling as the null space of this matrix, because it is nullifying this whole space, right? So it is annihilating the whole space and then pushing it to 0, right? So now remember, we started by looking at linear functions. Matrices represent linear functions, right? So which means that the sum of the input, I mean, I can add 2 vectors and then apply the matrix. That will be same as, applying the matrix to each of these vectors and then adding them up on the other side. Which means that I can take an arbitrary vector, let's say some vector x. Now I apply a, it will go to ax on the other side. Maybe that's not 0. But then now if I add to this input vector x any vector from this plane, now that's going to be a different vector on the left hand side. But then on the right hand side, it will still be the same vector as ax, because these vectors will get annihilated to 0. Right? So in other words, I'm saying a of x plus y is always ax plus ay. But then if y belongs to this plane, then ax plus ay is just ax plus 0, which is ax. Right? So which means that, you can add any vector from the null space to a vector, an arbitrary vector on the left hand side, and then apply a. It wouldn't have any effect at all. Right? It is as if you applied a to the original vector.
So you told ax plus ay equal to ax plus 0 equal to ax.
Yeah.
So always in the R2, in the 2-dimensional, the resulting point will be 0, 0, or it can be any point like 1, 1 or xy, any point. Means addition of any vectors in R3 will result in a
No.
point in the R2, or it is 0, 0 in R2. That's the question.
No. What I'm claiming is very, very simple, right? So I'm saying, let's say 1, 2, 3 was there. I applied a to 1, 2, 3, right? So now I get this vector. This is not a 0 vector, right? So this is 1, minus 2, 6, right? So this is 5, minus 5, right? So 1, 2, 3 gets mapped to 5, minus 5. Now I'm saying, if I add something to 1, 2, 3, which is in this plane, and then apply a, it will still go to 5, minus 5. That's all I'm saying. Why? Because 1, 2, 3 plus, let's say, some vector y, which is from that plane, that is not 1, 2, 3 anymore, right? So that's somewhere else. Now, if I apply a to this 1, 2, 3 plus y, it will be a times 1, 2, 3 plus a times y. But then a times y, a nullifies y, right? So y is in the null space of a. So that gets 0. So it is just the same as this. That's all I'm saying.
Got it.
Yeah. Any other questions?
So 0, 0 is not mandatory. It can be any point. Means what will be the output of 1, 2, 3? Only that point will be repeated every time. Whatever.
Correct.
Yeah. Okay. Thank you.
Yeah. So the same output you will not only get for 1, 2, 3, but you will get for an infinite number of vectors, right? So you can take 1, 2, 3 and add any vector on the plane. If you apply a, you're going to get the same answer. Yeah. Okay. So any questions so far with these two? Okay. Okay. So now on the left hand side, you see a plane, right? So it's a 3-dimensional input space. I mean, you could have taken anywhere in 3 dimension and applied a. A can be applied to any vector on the left hand side. But then if you apply it to this plane, it goes to 0, right? So think of this as the plane shrinks to 0, right? So, but then anywhere outside the plane, it's not going to shrink to 0, right? So because the plane is the only place where a takes the vector to 0. Anywhere else, it's going to take it to we know where. It has to take it to this line, x minus x line. This much we know about this a so far, right? Okay, good. Now let's look at the left hand side, right? So we have figured out where the null space is. So this is an important thing to remember. The null space is in the input dimension, right? Because it's on the left hand side. Now the right hand side, wherever in general A takes the whole R3, is what is called the column space, right? Because it's the linear combination of your columns, right? So your columns were 1, minus 1, which was this point, right? So 1 minus 1, I think minus 1 1. Minus 1 1 is here, and then 2 minus 2 is somewhere here, right? So if you linearly combine these, however hard you linearly combine, you are going to end up in this line only, right? So this is your column space. It cannot get your A, I mean, cannot get for no input, you are going to get something which is not on this line, right? So wherever you get your output, that is the column space. Okay. So in this particular case, this A is special in the sense
Sir,
that
not clear, sir.
All I'm saying is that I take the whole of R3, right? So that's what I initially did, right? So I mean, in this particular example, I took the whole of R3, right? So I took vectors randomly in R3 in all directions, but then the output was always in this line. Is that clear?
Yes, sir.
Yeah. All I'm saying is that no matter where I take a vector in R3, I'm not going to get anything outside this line. That's all I'm saying. Right. So where the output falls, that is your column space. Why is it the column space? Because the output is just a linear combination of your columns. Right. So on the combination, coefficients are given by your input vector. Right. So the moment I fix a vector in R3, it means that I'm saying that I have decided how I'm going to combine these columns. If that vector happens to be 1, 2, 3, then it means that I'm going to take 1 unit of column 1, 2 units of column 2, 3 units of column 3, and then add them. Right. So now, because all the columns are actually on the same line for this special matrix, no matter what units I take, I'm always going to end up in the line x plus y equals 0. I cannot go outside this line. Right. So the column space tells me where all I can end up in, right? So which means that outside this line, for no value of R3, I will get something outside this line, right? So because what is R3 telling me? It's just telling me how should I combine my columns, right? So but if my columns are all on the same line, no matter how I combine them or scale them, it's still going to be in the same line, right? So that's the column space. Is it clear now?
Okay, sir.
Or are there questions? Still questions?
So the thing is, in this animation, you are showing some from null space to column space.
No. This animation is not from null space to column space. The null space will always map to 0.
Yeah, null space is always map to 0, but when it will map to column space, entire R3 will map to the column space in R3.
Entire R3 will map to the column space, right? So this picture that I'm showing here, this arrow mark is not just for the null space. For the entire R3, if I apply A, it will go to the column space. These vectors in this plane will go to 0, 0. Right? So everybody not in this plane will go to somewhere in this line.
Yeah. So at max, we can go for column space only.
Yes, by definition, right? So that is the definition of column space. There, yeah. So it is the set of all x, set of all y such that ax equal to y for some x, right? So if I pick some point here, it means that there is some vector here which I applied a to, I'll get here, right? So I pick some point here, it means that there's some vector here to which I applied a, I got here. Right. So if I collect all the points from R3, then whatever I get end up on the right hand side is my column space.
Clear, sir.
Okay. Any other questions so far? Okay, good. Now, so if I look at this plane, right? So there is a left hand side, there is a plane in R3, which is what we are calling as null space. The right hand side, there is a line in R2, which is what we are calling as column space. Now remember, both of these are properties of the matrix A, right? So if I change A, all these are going to change, right? So this null space is specific for A, this column space is specific for A, right? So we derive this from the properties of A. That is something to keep in mind, right? So the null space is always input, the column space is the output. Now, let's look at the null space. I've just turned this around. It's still the same plane. Now, if I look at the null space or the column space, I observe that, well, there is some vector which is perpendicular to the null space. What does that mean? That means that no matter which vector I take in the plane, this vector 1, 1, minus 2 will make a 90° with that vector. We'll see how we got this 1, 1, minus 2. But then it's, I mean, if you have a plane, then it is not too hard to imagine that there should be a vector which makes 90° with every vector on the plane, right? So imagine that the plane is just the floor, right? So then that means that the z-axis will make a 90° with every vector on the plane, right? So if you tilt the plane, the z-axis vector is going to tilt a bit. So that's what is happening here. Now, because our null space is a plane, well, first of all, you can write an equation for it. We'll talk about the equation in a minute. But even before that, there is a plane, which is what we are calling as null space of A. And because it's a plane, there should be some vector which is making 90° with every vector with the plane, right? So in this particular case, that vector happens to be 1, 1, minus 2. That also we'll see why in a minute. That's one observation. Similarly, on the other side, the column space has a line, right? So it's just a line in 2 dimensions, which means that there is a vector again which is making 90° with everybody with the line, which is perpendicular to the line. In this particular case, it perhaps is easy to see what this vector is, because the column space we said is of all the vectors of the form x comma minus x, right? So which means that, you know, 1 comma minus 1 is there, 2 comma minus 2 is there, minus 2 comma 2 is there, and so on. So which vector makes 90° with all of these? Well, the vector 1, 1 or 2, 2, right? So anybody on this line would make a 90°, right? So this is one representative of this vector, but anybody on this line will make a 90° with the column space. Any vector along this line will make a 90° with the null space.
Why is it a single vector?
Why is it?
Why is it a single vector?
It's not a single vector, right? So I'm just illustrating a single vector. If you scale this by 2, I mean, the whole line will make 90°.
Okay, but can it move left or right?
One at a time, please. Yeah. So the previous question, yeah.
Yeah. Can we move it left or right? Can this vector?
Sorry, I'm unable to hear you.
Can this vector move left or right? We are talking about scaling, but can there be an offset? Can it move this side or that side?
So now let me ask you, the simpler way to imagine this is if you think the plane is the floor, right? So we know that the z-axis is one axis which makes 90° with every vector on the floor, right? So now even if you tilt a bit, then you lose that property of making 90° with everybody on the floor, right?
So, but there will be parallel lines to z-axis that will still make a perpendicular.
Correct. But in the whole of linear algebra, we are only going to care about lines which pass through origin.
Okay.
Right. So which means there is only one line in this case, in both these cases. Yeah.
Sir, I wanted to know the intuitive significance, like this null space is always perpendicular to the column space. There's a relationship between null space and column space.
No. Okay, so that's the common mistake that people make, right? So remember, in this picture, null space is a plane in 3 dimensions. Every vector there has 3 coordinates. The column space is a line in 2 dimensions. Every vector has only 2 dimensions, right? So you cannot talk about these two together, right? So they don't necessarily have any relationship or perpendicular relationship because they are in different spaces.
But in the lecture, we were taught that it's like the spaces are perfect. Like
I'll come to that. Yeah. I'll come to that. I think you misread some of the things in the lecture. Yeah. So
column space is not perpendicular to null space, I guess.
Correct. I mean, it cannot be right. So they are different. They live in different worlds.
In the lecture itself, the column space is perpendicular to null space of A transpose.
Okay.
Yeah, that is Rose.
Okay. So yes. So we are getting ahead of ourselves, right? So this picture should make it very clear that you cannot talk about orthogonality relationships between null space and column space at all, right? Because they live in different worlds. Null space is in the input world, column space is in the output world, right? So you cannot combine these two things at all, right? But what we do observe is that there is some vector which is perpendicular to the whole of null space, and then in this case there is also some vector which is perpendicular to the whole of column space. That is something that we are observing. Now, so we'll come to why these vectors, I mean, the column space, I kind of argued why this vector is 1, 1. Now let's understand why the null space vector should be 1, 1, minus 2, right? So the vector that is perpendicular to this null space of the matrix A. Okay, so for this, let's go back and see what this matrix A is. Now first, I mean, so what is the null space itself, right? So the null space is AX equals 0, right? So if I input an X, then the output should be 0. If it is 0, then X is in the null space, right? So A kind of nullifies the effect of X. So let's think of this X as X1, X2, X3, or rather X, Y, Z, right? So in 3-dimensional coordinate, X, Y, Z. Now, if I multiply A with X, right? So in your usual rule of multiplying matrices, right? So row times column. So it would be what would be the first coordinate of AX? If I multiply this matrix A with a vector X, Y, Z.
Sorry to interrupt. I mean, it's very difficult to visualize matrix multiplication when it comes to dimensions. Can you write a matrix so that we're able to understand?
Here is a matrix, right? So this is the only matrix we'll look at the whole of today. And then I'm saying, let's say I multiply it with 1, 2, 3. The simplest way to visualize matrix multiplication is as linear combinations, right? So you don't think of a matrix as some alien object, right? So it's just a bunch of vectors. Now, where are these vectors in this matrix? They are in 2 dimensions, right? So now there are 3 vectors in 2 dimensions, and then you are linearly combining them. That's all, right? So in this particular case, the vectors are all along this line. So no matter how I linearly combine them, I'm going to get something in that line. Is that visually clear or no?
Yes.
Yes, sir.
Okay. So in general, that's one good way to think about matrix multiplication, right? So when I say A times X, it simply means that I'm linearly combining the columns of X. Think of where the vectors of the matrix A are. They are in some space, right? So 3-dimensional, 2-dimensional, 100-dimensional, doesn't matter. But then I'm linearly combining them, right? So I'm scaling them and adding them. What am I scaling them by? Well, that is what my input will tell me, right? So the first coordinate of my input will tell me that the scaling factor for the first vector, first column, and so on, right? So and then I'm adding them. Is that clear? Or
Yes.
Okay. So now what I was trying to see is, now I want you to think about, if I give us input X, Y, Z to this matrix A, don't even visualize this time. Just think of the input as X, Y, Z, right? Now tell me what would be the first coordinate after you apply A to this matrix, AX. A times
X minus Y
X minus X.
X minus Y plus 2Z.
X minus Y plus 2Z, right? So because I'm going to multiply this vector with X, this vector with Y, this vector with Z, and then add them up, which means that the first coordinate would be X times 1, the second coordinate plus Y times minus 1 plus Z times 2, right? So which is X minus Y plus 2 times Z, right? So, and I know that the second coordinate has to be the negative of that, because that's what this matrix satisfies, right? So the output would be X minus Y plus 2Z, and similarly minus of X minus Y plus 2Z. Now, if this XYZ has to be in the null space, then it means that this value is 0, right? So which means that's exactly what I've written here. X minus Y plus 2Z has to be 0, right? So any vector in the null space, if I apply A, will go to 0, which means the equation of any vector in the null space should necessarily satisfy X minus Y plus 2Z equals 0. Is that clear?
Yes.
Everybody?
So X minus Y plus 2Z equal to 0, and also minus X plus Y minus 2Z equal to 0. Both
Are these two things different? Because the second one is minus
sign.
Yeah.
Minus.
Same.
It's the same.
Both are same.
Both are same, right? So which means there is only one equation, right? So which is the equation of this plane?
Okay.
Right? So the null space itself, I can write it as X minus Y plus 2Z equal to 0. Correct, sir. Is that clear to everybody?
Yes.
Yeah. So basically, I'm saying, well, we visually saw that this is a two-dimensional space. I'm now trying to argue why this equation of this plane has to be x minus y plus 2z equal to 0. Right? So that's because, I mean, if for an arbitrary vector x, y, z, ax would be x minus y 2z, x minus y plus 2z, and minus of x minus y plus 2z. If it is in the null space, then both these components should be 0, which means that the equation that any vector in the null space should satisfy is x minus y plus 2z is 0. Fine. Now here is the interesting part, right? So when do you call two vectors as perpendicular? Let's say you have a vector A and vector B.
Angle is 90 degrees. Slope.
Yeah.
When the dot product is 0.
Yeah. So when the dot product of angle is 90 degree in 2 dimension, but then in general, if the dot product is 0, then it means that those two vectors are perpendicular. Is that something that you are intuitively able to see why?
Yes, sir.
Everybody, is that clear? Why A transpose B should be 0 if A and B are perpendicular?
Excuse me, sir.
Yeah.
Sir, here I have a question. In 2 dimensions, we can say perpendicular, but in more than 2, do we keep saying perpendicular, or is orthogonal the correct term?
Orthogonal is the correct term, right? So I'm just using perpendicular loosely here. So the correct term is
got it, sir.
Right. So yeah, so because the angles are much more trickier in higher dimension, so we'll just deal with orthogonality there. So I'm saying if you take two vectors A and B, then we'll call them as orthogonal vectors. In other words, in 2 dimension, they will be perpendicular if their dot product is 0. Right. So what is dot product? Well, you have vector A1, A2, A3, B1, B2, B3. A1 times B1 plus A2 times B2 plus A3 times B3 is 0. If that happens, well, then the vectors are actually perpendicular to each other. I'll talk a bit about why that should happen a little later. For now, I mean, if you're not visually convinced why that is the case, for now, take it for granted, and then I'll come back and after finishing this sequence of slides, and then I'll come and argue why that should be the case visually. Okay. So now here is the interesting way to look at the null space, right? So what we are saying is that the null space is the set of all vectors x, y, z such that x minus y plus 2z equal to 0. That is the equation of the null space. Equivalently, I can say that this x minus y plus 2z is just the dot product of x, y, z with 1, I think I should have done this the other way, 1 minus 1, 2, right? So in fact, this is, okay, so this should have been 1 minus 1, right? So why? Because if you do the dot product of 1 minus 1, 2 with x, y, z, then you will get what? X minus y plus 2z. If that is 0, then it means that, well, this whole plane has to be perpendicular to 1 minus 1, 2. Right? So which means if I give you a plane and an equation, if I describe a plane with the equation, then immediately you can say which is the vector that is perpendicular to this plane. Right? So on that vector is exactly just, you can read out the coefficients of x, y, and z, right? So 1 minus 1, 2. Because 1 minus 1, 2 dot product with x, y, z is just x minus y plus 2z, which we know for the null space is 0, which means that that vector 1 minus 1, 2 should be orthogonal to the null space. Does it make sense?
Yes.
Makes sense.
Okay, cool. Okay, so now what we have kind of established now is, we have null space on the left-hand side, column space on the right-hand side. The null space has a vector perpendicular to it, which is 1 minus 1, 2. And the column space has a vector. When I say vector, it's the whole line, right? So you can scale it, and then dot products is still 0, right? So A transpose B is 0 means A transpose 2 into B is also 0, minus 2 into B is also 0. Everything is 0, right? So the whole line will be perpendicular. Similarly, on the right-hand side, we have the column space whose equation is x plus y equals 0, which means that you have the vector 1, 1, which is perpendicular to the entire column space. Again, you can read out the vector just by looking at the coefficient of the equation of the column space, right? 1, 1. Good. Now these vectors look arbitrary. Now we'll just keep this at the back of our mind, that null space has a vector perpendicular to it, column space has a vector perpendicular. We'll revisit this later. Now what we are going to do is we are now going to slightly shift gears and then look at not A, but then the matrix A transpose and see what happens to A transpose, right? So A transpose is a 3x2 matrix, right? So A is 2x3, which means A transpose is a 3x2 matrix, right? So I mean, all of us know what a transpose is, right? So you flip the rows and columns. Now, which means it's going to map two-dimensional vectors to three-dimensional vectors. A was mapping three-dimensional space to two-dimensional space. A transpose would do the opposite. It would map two-dimensional space to three-dimensional space, right? So now I can go through the same procedure that we tried for A, which means where I'm going to randomly pick vectors from 2 dimension and see what would happen on the other side, right? So what I'm going to do here is I'm going to pick arbitrary vector in 2 dimension, which you'll see on the left-hand side. Now, what would be your guess as to what would happen on the right-hand side, even before I play this?
Line again.
Is that a guess or a...
Yeah, because it's the same thing, right? The columns are still dependent, or the coefficient will, same line will be scaled, but both will scale the same line, 1 minus 1, 2.
Mm-hmm.
The output was going to be R3 now.
The output is going to be R3 now. That's good. Yes.
It's a 3-dimensional output. And
Yes,
it
yes,
kind of does reverses whatever we saw before.
No.
I think output will be R3, but it'll still be a line because both of those columns are nothing but one is linear combination of the other. So it will span along that line itself, I guess.
Mm-hmm. So what you're saying
Right.
is that the first column is kind of the negative of the second column. So both these, so if I think of these as vectors in R3, then they are in the same line. So which means how I combine them using vectors in R2.
Yes, sir.
Yeah, it doesn't matter. It will just go along that line.
Okay, let's actually see that to convince ourselves that it is indeed the case, right? So when I, for instance, if I kind of fix this vector here, right? So it means that this is somewhere pointing at minus 0.251, right? So which means that I'm multiplying minus 0.25 with the first vector and 1 with the second vector. But then these two guys are in the same line, which means that no matter how I combine them, they have to be in the same line, right? So something similar happens like what we did the previous time, just that now we are mapping from 2 dimension to 3 dimension. Now in 2 dimension, I'm looking at the entire R2. The entire R2 gets mapped to a single line in R3, right? So that's because these two columns are in R3 are essentially, they lie on the same line. Is that clear? I mean, why this should happen? It's the same argument. Okay. Now what is this line, right? So if you look at which line is this, right? So this line has to be some combination of these two vectors, right? So some combination of these two vectors will necessarily be the same, I mean, along the same line as the first vector, right? Because the second vector is just the flipped version of the first vector, they lie along the same line, which means however I combine them, it has to be along the line of 1 minus 1, 2, right? So, okay, again, I've made a mistake here. So this is 1 minus 1, 2, but then this line itself is 1 minus 1, 2, right? So is that clear why this should be 1 minus 1, 2?
So if the second column is not the any linear multiple of the first column, then we will have a 2D representation.
Yeah, so that's a good question. If the second column is not a linear, is not the scaled version of the first column, then the points will still be in 3D, but then it will be in a plane.
Yes.
Right?
Okay.
Yeah. Because from 2D, you cannot reach all of 3D. Right? So you'll only reach a plane.
Okay.
Yeah. So, but now because in this special case, they are just both multiples of each other, you fall on a line, right? So this is fine. So now here I took arbitrary vectors on the left-hand side, and then I saw them getting mapped to this line. Now here is another thing where I won't take arbitrary vectors. I'm kind of taking vectors in a special way, right? So I'm taking vectors along a particular line, and then what I'm observing is that they all map to the 0 vector, right? So we did, this is exactly the same thing that we did before, right? So we took arbitrary vector first and then saw that for A, they map to, a line in R2. Here, they map to a line in R3 because it's flipped. Now I'm taking vectors only along the line, a particular line, and then I'm observing that if I take vectors along this line, they all map to the 0 vector. If I apply A transpose, right? Now, what is this then? What is this? What should we call this line?
Null space.
Null space of A transpose.
Yeah, so null space doesn't make sense on its own, right? So it always has to be tied to a matrix. So this is the null space of A transpose now, right? So the null space of A transpose is along the direction of 1, 1, right? So that's what we are seeing. And we also saw the column space of A transpose is along the direction 1, minus 1, 2, because it's just combining the columns. Now this 1, minus 1, 2 and this 1, 1 are not arbitrary vectors, right? So we already met these vectors before when we are discussing A itself, right?
Excuse.
Yeah.
So how you are saying that it's along 1, 1, 1 or 1 minus 1, 1 minus 2 like that?
This one.
Yes,
why is it 1, minus 1, 2, right?
So how you are saying that it is along 1, 1 minus?
Yeah. So what does it mean to say I am applying A transpose to a vector X, right? So where is the vector X? The vector X is in 2 dimension, right? So because A transpose maps 2 dimension to 3 dimension. So the 2-dimensional vector will have 2 coordinates, right? So x1, x2. Now, when I apply A transpose to x1, the vector x1, x2, it is going to multiply the first vector by x1, the second vector by x2, and then add them up. But now for this particular matrix, the first vector and the second vector are on the same line, which means if I scale them, they will again fall on the same line. If I add them, they'll again fall on the same line. And that line is basically the same line where these vectors live, right? So they cannot escape this line. And that's why I'm saying the column space of this has to be 1, minus 1. This has to be 1, minus 1. Does that make sense?
Yes, sir. Okay.
Okay. Okay. Any other questions? Okay, so we have seen the null space of A transpose also. We have seen the column space of A transpose also now, right? So now let's kind of try to
put one question, sir.
Yeah.
So in the previous set, A was there. A was 1, minus 1, 2, minus 1, 1, minus 2. So from there, for that A, we moved from R3 to R2. Now you are transposing A 1, minus 1, 2 and minus 1, 1, 2.
Correct.
So means what should be the dimension of X so that it moves from R2 to R3? It is like X1, X2, X3 on a single row?
Sorry, say the last 2 lines again.
Means what should be the dimension of input vector X so that it converts from R2 to R3? Like
yeah,
previously you told means from R3 to R2 because X1, X2, X3 in a single column. But here in this scenario, it will be X1, X2, X3 in a single row. For that, it will move from R2 to R3. It will map from R2 to R3 for A transpose.
Yeah. So whenever you have a vector, matrix A, right? So which has some number of rows, some number of columns, right? So your input should always be equal to in the dimension equal to the number of columns. Only then you can do multiplication meaningfully. Right. So because why? Because you need some scalar multiple of each of these vectors, which you will first scale them and then add them up. Right. So that's what matrix multiplication with the vector means actually. Right. So which means that if you have 3 columns, then your input should come from R3. If you have 10 columns, your input should come from R10. Now for A transpose, you have only 2 columns. So your input should come from R2. Right. So maybe the input is 5 and 10, which means that I am multiplying the first column by 5, second column by 10, and then adding them up.
Okay, sir. Input is coming from R2, that's clear. But how it is going to R3?
So what is happening is that the input tells you the weight, think of it as some weight it gives to each column, right? So, and then you are doing a weighted sum of the columns, right? So, but where are these columns? The columns are all in R3 for A transpose, right? So for A transpose, this is a vector in R3, this is a vector in R3. So there are two vectors in R3, and now you are combining them. Now, how you want to combine them is what your input is telling you. Right? So no matter how you combine them, you are going to be in R3 only.
Okay.
Is that clear to everybody? I think that's yeah.
Sir, in the first matrix, that A, if there only one column is linearly independent, rest two are dependent column with the other one. If instead of that 2 is independent, then we will line to the plane, right? Instead of line in the column space.
Perfect. Yes.
And if it is 3, then I will line to the same R3 to R3.
Can you have 3 independent columns in this matrix?
No, in this matrix I can't.
Why can't? Why you can't?
Because the third coordinate is not there. It can only go up to 2.
Yeah, so that needs an argument, but yeah, you are right. Right. So these are vectors in 2 dimension, right? So think of these as column vectors. You have 3 vectors in 2 dimension. They cannot all be linearly independent. You can only have maximum of 2 independent vectors. Yeah. Okay. So I think there was one interesting question in the chat box, and we try to read that out. So in the previous example for 1, -1, 2, it is visually clear from the figure that it is perpendicular to the null space at a particular point. But how is it perpendicular to all the points in the null space, right? That's a good question. So now, so I take any point here, any point here, any point here, any point here. The question is, how is this vector, which is pointing outside this plane, perpendicular to everybody in the plane, right? So that's the question. Now here, well, visually one can see this, but then mathematically the argument is that, well, what does perpendicular mean? It means that if you find a vector A such that A transpose B equals 0 for every B in the plane, then you're done. Now I'm claiming that this 1, -1, 2, this should be 1, -1, 2. This 1, -1, 2 vector is orthogonal to every vector in the null space. Now, every vector in the null space, every vector x, y, z in the null space satisfies x minus y plus 2z equal to 0. By the virtue of the fact that it satisfies this equation, I can rewrite this equation as the left-hand side of x minus y plus 2z as simply the dot product of 1, -1, 2, the vector 1, -1, 2, and the vector x, y, z. Which means that if that by definition, you can define the null space as simply the set of all vectors which is perpendicular to 1, -1, 2. Right? So that's what dot product means. Does it make sense?
Sir, the vector it might not be 1, -1, 2. Sir, can you just check?
Why is it?
Sir, if you could just take any vector in the null space and just multiply the dot product is not going to 0. Just take a sample number and it is not going to 0. Even if you take 1, -1, 2 also, it will not go to 0.
What is a vector in the null space? Give me a vector in the null space.
-1, -1, and the third one, somewhere it went. If you look at the previous diagram, I would.
No. Look at this A and give me a vector in the null space.
So 1, -1, 1.
1, -1, 1.
That does not satisfy the equation.
That does not satisfy Ax equal to 0, right? So if you have 1, -1, it has to be -1. Isn't it? So what does 1, -1, 1 do to A? Right? So it will be 1, -1 plus 1, -1 plus 2, -2. That would be 4, -4, right?
So I'm just trying to satisfy your equation in that image. Previous image, there was an equation, right? I'm just trying to put some number which satisfy that equation.
Which one?
This equation, x minus y plus 2z is equal to 0.
Okay.
We put x as -1. I put y as 1.
Okay. No. You initially said 1, -1. Now what are you saying?
So x is -1, y is 1, and z is 1.
Okay, so this, so minus 1 plus 2z, right? So yeah, so this is fine. Okay, so now I'm saying multiply this with 1 minus 1 2, right? So it is not 1 1 minus 2, right? So that's, so this is what I want you to correct, right? So this vector is actually 1 minus 1, right? So now if you multiply your vector that you gave me, which is minus 1 1 1, take the dot product with 1 minus 1 2, you will see that is 0. Does it make sense?
Okay, sir. Yeah, now it is clear.
Yeah. No, okay. So I think you should simply be able to read it out from this, right? So by definition, I'm saying x minus 1 plus 2z equal to 0. I'm just going to, in a fancy way, write this x minus y plus 2z as just the dot product of x, y, z with 1 minus 1, 2. Which means that all I'm saying is that by defining null space as this, equivalently, I'm saying that it is perpendicular to the vector. Anyway, any vector in the null space is perpendicular to 1 minus 1, 2. Okay. Okay, good. So, so now let's just move quickly on. So what we have done so far is the following, right? So this is the big picture that we have now, right? So when I move from R3 to R2, right, I had a null space of A which was getting mapped to 0, which satisfied the equation x minus y plus 2z equal to 0. And the column space was the set of all vectors which satisfied x plus y equals 0. Now the vector that is perpendicular to the null space happens to be the column space of A transpose, right? So that's what we saw here, right? So when we did this, A transpose was mapping 2 dimension to 3 dimension, which means the column space of A transpose was exactly the same vector, which is perpendicular to the null space of A. Similarly, the vector which is perpendicular to the column space of A is simply the null space of A transpose. So these vectors which are perpendicular are not arbitrary vectors. They define the column space of a different transformation which is associated with A, which is the A transpose transformation, right? So basically what we are saying is that if you, for any, this is for this example, but then I think what was proved in the class would have been the fact that you can take any transformation A. Now you can look at its column space and null space. Now the space that is perpendicular to the column space is exactly the column space of A transpose. And the space that is perpendicular to the column space of A is exactly the null space of A transpose, right? So these are the 4 fundamental subspaces, essentially, whatever you're seeing in this picture. Just to give a high level view, at least is the understanding slightly better now? Or I'm sure if you're looking at it for the first time, you might have more questions, but yeah.
Yes, sir.
Sir, one question, column space of A transpose as you've shown in the left side, it will always lie on a line.
For this A, yeah.
For this A. And the null space is a plane.
Again, for this A, right? So if the column space becomes a plane, the null space will become a line, right?
Column.
So,
space.
So if for a different A, if the column space was a plane, right? So the columns, because it's A transpose is a 3x2 matrix, right? So the column space is either a line or a plane, right? So because you only have 2 vectors, and then you are linearly combining these 2 vectors. If the 2 vectors are on the same line, then you will get a line of A transpose. If the 2 vectors are not on the same line, then you will get a plane, right? So if the 2 vectors are not on the same line, your column space of A transpose is going to be a plane. But then if you look at the null space of A, it would be a line, because it has to be perpendicular to the column space of A transpose, right? So this is in fact your rank nullity theorem, right? So these 2 guys have to add up.
Yes.
So it's like when you have 3 dimension and 2 dimension, like if your vector, it's like there's a 3-dimensional space, the null space would be a plane.
So
I'm a bit confused about this. Like
I think
if it's a 4-dimensional matrix.
So you cannot argue anything just by saying the dimension of the matrix. That's the whole point here, right? So it depends not only on the dimension of the matrix, but then the dependency of the vectors in the matrix, of the vectors of the matrix, right? So for this particular matrix A, all the vectors are on a single line. And so you see this picture. If I change the matrix A, the picture will change. But then what does not change is the fact that the null space of A has to be perpendicular to the column space of A transpose, and the null space of A transpose has to be perpendicular to the column space of A. That relation always holds. But then whether these are planes or lines depends on how many linear vectors do you have in A itself, right?
Okay.
So, sir, it is not mandatory that null space of A should convert to column space of A. Means should convert to when we are going from the R3 to R2, null space of A should not be a plane and column space of A should not be a line. It depends on the coefficients of A matrix that decides how it looks. If there is no linearly independent columns are there, then automatically the null space of A will convert in a plane. In the column space of A in 2D will convert into a plane, not in a line. You're saying that?
That's what I'm saying. You have to look at the linear dependent structure of the vectors of these columns. Now here is one way to also think about it. Right? So let's think about the easier case where you have a 3x3 matrix. Right? So this is a 3x2 matrix, but then if you just have a 3x3 matrix, now if all the vectors are linearly independent, you can have maximum three linearly independent vectors. Let's say where all the three vectors are linearly independent, right? So then your null space would just be, the zero vector. There is nothing else that will map to zero. It will only be the zero vector, which means the column space of A transpose would be the entire R3. Now, similarly, the column space of A in that case, because you have three linearly independent vectors, they will span all of R3, right? So the column space of A on the right-hand side, which will be R3 now, because it's a 3x3 matrix we are talking about, would be the entire R3, which means the null space of A transpose, which has to be perpendicular to the column space of A, will just be the zero, right? So it means that the only vector that maps to zero is the zero vector itself, nobody else, right? So when that happens, the matrix itself becomes invertible, right? So otherwise you don't know, what does invertibility mean, right? So if I give you one on the right-hand side, you have to tell me where it came from the left-hand side. Now, if there is a null space, then I don't know which vector came mapped to the right-hand side vector, because I could have added any vector from the null space, right? So there is no one-to-one mapping between left to right, right? So if the null space has higher dimension than just the zero vector, then the matrix does not become invertible anymore, right? So that's the idea. I hope that is clear.
Yes, sir.
Sir, can you please come back again how you told that row nullity theorem, like you related row nullity theorem from this? Like I missed it.
Not row nullity, rank nullity theorem.
Sorry, my bad.
Yeah. So basically, rank nullity theorem, just what is the rank nullity theorem, right? So what is the rank of a matrix? The rank of the matrix is the dimension of the column space of A or the dimension of the row space of A, right? So the row space is just the dimension of the column space of A transpose, right? So here on the left-hand side, right? So you have R3. Now what we are saying is that R3 can be written, that number 3 can be written as 2 plus 1, where 2 is the dimension of the null space and 1 is the dimension of the column space of A transpose, right? Which is same as the column space of A, dimension of column space of A also, right? So similarly on the right-hand side, you can write as null space of A transpose is 1 dimension, column space of A is also 1 dimension. So that 1 plus 1 adds up to 2 here, because this is R2. That's your rank nullity theorem, essentially.
Okay. So like how I was relating was basically, let's say there are like if all the three vectors are linearly independent, let's say A is 3x3. So then we can't basically there will be the column space will span complete R3.
Correct.
So we can't have any direction in which can span the zero vectors.
Which means what?
Like
The
we
null
can't have
space,
anything perpendicular.
what is the null space then?
The null space will be nothing but a zero vector in this case. So I was relating in this way.
That is correct. Then the null space is the zero vector, which means the dimension of the null space is 0. Right? So the dimension of column, which means that what is the column space of A transpose then? It will be the R3, right? So which will have 3.
Yeah.
3 plus 0 is 3.
Yeah.
It can either be 3 plus 0, 3, 2 plus 1 is 3, 1 plus 2 is 3, or 0 plus 3 is 3. All are okay.
So null space being empty and null space being 0 are not the same, right?
No. So okay, by the definition of a space, it has to have the 0 vector, right? So when I say there is no empty sets at all that we will discuss. Right?
So the nullity will always be 1 in that case for any space.
No. So if you only have 0, then we'll think of that the dimension of such a vector space as
0.
just 0, right? So because basically what is the dimension of a space? It is the number of linearly independent vectors that you can collect, right? So 0, 0, 0 is not considered by definition, it's considered not a linearly independent set.
Okay.
Yeah. Okay.
For 3 cross 3 linearly independent matrix, the null space is 0 and the column space is 3.
Correct.
For the transpose, column space of A transpose 3.
Why? Because the column space of A transpose has to be perpendicular to the null space, right? So what are the set of all vectors which are perpendicular to 0, 0, 0? Every vector is perpendicular to 0, 0, 0, right? So by perpendicular, I mean A transpose B is 0. And so the column space of A transpose will be the entire R3, and so its dimension will be 3.
Yeah.
Is that clear?
Yes, sir.
Okay. So before we move on to other things, any questions about this, the 4 subspaces?
So, sir, again repeating the last one, for a 3 cross 3 linearly independent matrix, we will map from R3 to R3, and in the null space in the input R3 will be, if the null space in the input R3 is a point, then the column space in the output R3 will be the entire R3 plane.
Okay, so the null space, yeah. So if you have 3 independent vectors, then the column space will be, the number of independent vectors you have in your matrix will determine the column space dimension.
Right.
Right. So which means it will be the entire R3. Entire
R3, correct. And the transpose, if you are transposing the A, then the null space, not null space, the column space in R3 will be a point in the output R3. The null space will be a point in the output R3. Am I correct?
Can you repeat your statement again?
So I repeat from the beginning. Let's say we have A is there.
Okay.
So for mapping with A, we have input R3. If the null space is a dot, is a point, then in the output R3, the column space will be the entire R3.
Correct.
For A transpose mapping, if the column space is it's the entire R3 in the input, then in the output the null space will be a point, a dot.
Yeah.
I'm correct,
so
sir?
you're perfectly correct.
Okay.
Yes. Yeah.
So and you are saying that the number of linearly independency means the number of linear independent vectors decides this relative numbers, that the one in input will become 3 in output, 3 in input will become 1 in output. It's like that.
Now what I'm saying is that given a matrix A, first start looking at the think of matrix as a bunch of vectors and see how many linearly independent vectors can you find.
Right.
So if it's a 3 cross 3 matrix, and if you find only one linearly independent vector, like how we would, it's a 3 cross 3 matrix, this is 3 cross 2, but then let's say 3 cross 3 matrix, but then there is only one linearly independent vector, right? So which means that
if one linear independent is there, then 3 will become 2. Means entire three-dimensional will become a two-dimensional in output.
No. So the matrix is 3 cross 3, right? So which means that the input is R3, output is R3.
R3.
But then this is not any matrix. This matrix has three dependent columns, right? So there is only one independent vector.
Right.
Let's say the other two are scaled versions of this, right?
Right.
So now, which means that no matter how you combine them, you're going to get only a line in the output.
Right.
So which means that if you have only one independent vector in the matrix, then your column space dimension will just be 1.
Right.
If you have 2 independent vectors, your column space dimension will be 2. If you have 3 independent vectors, your column space dimension will be 3. So the number of independent vectors in your matrix is exactly same as the dimension of the column space. Independent columns, right?
And
so
what about A transpose?
Yeah, so A transpose would be the opposite, right? So you'll have to look at the number of independent rows, and that there is a theorem, right? So I think that was argued in the class. I'm not sure.
Yes,
right?
yes,
so the number of independent rows would be always same as the number of independent columns, right? So though even if the matrix is M
transposed,
right? Even if it's transposed, right? So which means that if you had 3 independent columns, then you will have 3 independent rows.
Okay.
Yeah. So that would be the same dimension.
So for A transpose, as you told that if one independent is there, then it will become a line. If 2 independent is there, it will become a plane. If 3 independency is there, then it will become a entire R3 space. And if you are coming to the reverse A transpose, then the same. But but in this case, the column space will convert into null space in this case for A transpose.
I mean, so you have to be careful about what the column space is, right? So the dimensions are the same, but then the planes might be different, right? So let's say I have 3 cross 3 matrix, but then with only 2 independent columns, right? So now my column space will be a plane. Now, if I do A transpose, the column space of A transpose will also be a plane in R3 only, but then these 2 planes may not be the same. Only the dimensions will match, but then the planes will be different. Could be different.
Correct, sir. I'm getting that that A transpose, the planes will be different because our mapping function is different here. So
exactly.
Ultimately, the plane will be different. That's okay. But what I'm saying that the conversion is that if number of independency is 3, it will go to the 3. If number of independency is 2, it will go to 2, means it's a plane. If the number of independency is 1, then it will go to 1, means that's a point.
That's a line.
Sorry, that's a line. So columns for A transpose, column space in the input column space will become for one independency. For one independency, the input column space will become a line. The null space will become a line. For 2 independency, the null space will become a plane, and for 3 independency, the null space will become the entire R3. That's the thing, sir. Okay,
it's the same, right?
Clear, sir. Okay, that's it. I was just repeating.
Yeah, no problem. Okay, so I hope this is clear. Okay, so I'll kind of go back to my tablet here. So these are the slides that I had. I could not prepare too many given time, but hope this is visible. Okay. Okay, so what should I do next? Is there a
projections?
Projections. Okay. So now that you know these things, projections will be very easy, right? So I'll give you a high-level view of what projection is trying to do, right? So so let's do the simplest case first. Let's say I am in R2, right? So and I have some vector u, which is u1, u2. Now I have the span of u. The span is a fancy way to say that you look at all combination, all scalar multiples of this vector, which means this whole line, right? So this is span of u. Now I have some other vector here, which is V, which is V1, V2. Now I want to ask the question, where, so if I want to choose a proxy for this V along the line of U, which point should I choose as a proxy? This is the question we want to ask. So I'll later motivate why choosing a proxy might make sense. But for the moment, let's say for some reason this is important, and we want to understand where should I choose a point on the blue line, which can act as a proxy for V, right? So I give you some options. So is this point? Is it this point? Is it this point? Or is it this point? A, B, C, D. Which one would you choose?
B.
B1.
Okay, why?
Because its length will be closer to the V. I mean, among all the possible ones, that will be closer.
Okay, so somehow we are saying that this length is, if I project, if I think of this as my proxy for V, then the length is low, right? So if I think of this, then I'm kind of missing out a big chunk, which is larger. So I will pick the one that is as small as possible, right? So now whatever that point is, we want to figure out what that point is, right? So now we know that this point lies along the line spanned by U, right? So which means that this has to be some constant times U1, U2, correct? So it has to be some constant times U1, U2, right? So now, which constant it is, right? So that's the question. As I vary the constant, the points along the blue line changes. So for some constant, it exactly is closest to V, right? So now I can ask the question, which is the point which is closest to V, right? So for which value of C does this become really, really close to C? But what does close in what sense? Well, the length of this missing piece, the piece that I lose, right? So because if I'm going to think of this as the proxy of this black dot as the proxy of, as the green vector, then it means that let's call this some W. Then it means that my V itself is W plus this blue piece, right? So this blue piece would simply be V minus W, right? So which means this vector, this is V minus W, right? So if I take this vector V minus W and keep it on the head of W and then add them up, I'll get V, right? So, and I want to find that V minus W, which is as small as possible in terms of length, right?
Can you repeat the V minus W part? Quite lost to this.
So vectors, so basically, okay, let me remove the other things which are not needed. Yeah. So this is a vector, right? So now this is what. So this is what I need to add to this brown vector to get the green vector, right? So, but then vectors will all start from the origin, right? So which means that I have to add this, right? So when I add two vectors, A and B, then what does that mean? That means that I'm keeping B here, and then this is the vector that I get, right? So that's how vector addition works. So which means that, as I choose these various points, then the vectors change, and then I want to find one which has the least length, basically, right? Is that clear?
Yes, sir.
Okay, great. So now I want to understand which is the C which does this, right? So that's the question that I want to ask. Now, which means that I want to find a minimum over C. Somehow we want to minimize the length of this blue piece, which is V minus W, right? So, or length squared, doesn't matter. Length squared is typically easy to minimize of the vector V minus W, if I think of this as W, basically. So what is V minus W? Yeah.
Why are we moving backward? I mean, can we also do it on the other side? If
Meaning?
The positive. Or are we doing it this small vector that you've drawn, the V minus W1? So is it because it is starting from the origin? Or why have you taken this vector and not the mirror image, which is on the positive side, positive quadrant?
This one? No. Which?
The other one. So The one in the first quadrant. You can take a point, a vector that is parallel to this in the first quadrant, right?
Parallel to what? When you say this,
V minus W. Yeah.
So this vector, right? Yeah. So this is the vector whose length we are trying to minimize. Okay. So I think, okay, all I'm saying is that, so let's take an example. I think numbers are easier. Okay.
No, in that diagram, sir, so brown and green vector were to be added. So I always assume it as a parallelogram, and the end of the other diagonal of the parallelogram is the added point. That's how I visualize it. Am I wrong with that?
You mean the addition of vectors, right?
Yeah.
Yeah. So if I'm adding this vector with this vector, then it means that this is the head of the tail of first. The second vector should sit on the head of the first vector, right?
Correct.
So you keep it here, and then you get this point. Correct.
Oh, so we are not adding the green and the brown.
No. I need to get the green, right? So this is. So I'm going to think of W as a proxy for V, which means that I'm asking what should I add to W to get V, right? So and that is V minus W, and I don't want to miss too much, right? So I want to get as small as possible, right? So that's what I need to add. I need to lose as low as possible. And so I will try to find that C. As I vary C, so I'm going to vary along the line in the direction of U. So I will find a C such that C into U1 minus U2, which is my W. And then I have V1 minus V1, V2, right? So this difference vector, which is V minus W, right? So W is C times U1, U2. I don't know for an undetermined value of C yet, right? So as I change C, now this missing piece kind of keeps changing. Now I want to find that C which has the minimum length.
Got it.
Length squared, let's say. Now this is a vector in itself, right? So it is just V1 minus C times U1, V2 minus C times U2. That's just the subtraction of these two vectors, right? So now I want to minimize the length squared of this vector. C is the one thing that I have handle on. I can change C as I want so that the length squared changes. And I want to find that C which minimizes this, right? So now how do we define length squared in Euclidean plane? What is the length of a vector? So let's say this is
square of both the coordinates.
Yeah. So this is A, this length is A, this length is B. So the length of this by Pythagoras theorem should be A squared length. So then squared is A squared plus B squared. So you take a square root. So that would be your length. But then length squared is just the square of this, right? So so that's the definition of, that's one definition of length. I mean, but for now it suffices for us. I mean, at least the basic level, we'll just assume that's the length definition. So you want to minimize over C, then it means that V1 minus C U1 squared plus V2 minus C U2 squared. Okay, so once we get C, then we know what is the answer, right? So we know C times U1 U2 is the answer, that we know. Now, how would we minimize this or to find the best C?
Partial differentiation.
You don't even need partial differentiation. It's just a function of one variable C, right? So it's just
just differentiation.
Just differentiation. So if I do the differentiation, so then what would I get? So this is minimized over C, V1 squared plus C squared U1 squared minus 2 C U1 V1 plus V2 squared minus plus C squared U2 squared minus 2 C U2 V2. Now I take the derivative with respect to C. So think of this as f of C. C equal to f dash of C. Well, 2C U1 squared minus 2 U1 V1 plus 2C U2 squared minus 2C. If you're not following this, it's just basic differentiation, nothing fancy going on here. U2 V2. And now what do? I set this to 0 and then solve for C. If I solve for C, what I'm going to get is U1 V1 plus U2 V2 by U1 squared plus U2 squared. This is a number, and this is saying that how much should I scale U so that I get the point which is closest to V, right? So this is a function of both U and V. Right? So U determines where I am finding the proxy for. V determines which vector I'm finding the proxy for. The sanity check that depends both on U and V. Right? So the point itself then is u1 v1 plus u2 v2 by u1 squared plus u2 squared times u1 u2. Now this is the vector, right? So this was u, which was u1 u2. Now I scaled it, so this is my v, v1 v2. I find this point, this happens to be exactly this vector, right? Now this should sound familiar. You can kind of try to generalize this to higher dimensional vectors, not just 2 dimension. Now this guy is just our familiar u transpose v, right? And then this is basically norm u squared, and then this is u, right? So basically, now what we have essentially done here is we have projected the vector v along the direction of u, right? So that's what we have done, right? So now the question is, I give you v, and now there is this projection, and out comes u transpose v into u by norm u squared, right? So this is the projected vector. This is the input, right? So now is there a matrix P that does this for us, which takes as input v and then outputs the answer? Now, if you rewrite this a bit, you will see that this P is just u transpose by u transpose u, which is norm u squared. Why? Because now P times v will be u transpose times v by u transpose u, which is u transpose v into u by u transpose u, which is norm u squared, which is exactly what we had here, right? So what we have kind of derived now is, the projection matrix, which takes a vector v and then projects it on to the span of u, right? So which is just exactly this matrix. This is a matrix. Okay, so if you're not played around with this enough, it might take some time to get used to the fact that u transpose u is a number, but then u transpose is a matrix, right? So this is a matrix. This is just a number. This projection itself is just a matrix divided by a number, which is dividing all the elements of that matrix by this number.
So can you repeat the v projected to this u transpose v by norm u squared into u? From there,
Okay.
how did you arrive at jump to p is equal to u transpose?
Correct. So what we proved is that if you start with v, right, so and then you want to project it along the direction of u, what you get is that u transpose v by u transpose u, which is just norm u squared into u, right?
Correct.
This is what we got. Now, so this is some vector in d dimension. This is also some vector in d dimension. Now I'm asking the question, well, is there a matrix which will do this for free for me, right? So if I input v, is there a d cross d matrix which will take as input a d dimensional vector and then output, u transpose v by u transpose u times u. Now this guy, right? So this is a number. U transpose v by u transpose u is a number times a vector. This is an RT. Now I can rewrite this because I need this p to be a function of u, right? Function of v, right? So v is the input. So everything else, should come out. And I mean, I'm trying to separate the u's from the v's, if you will, right? So what I'm saying is that the same thing, I can write it as u transpose v by u transpose u. Nothing changes, right? So I'm just writing the number, which is u transpose v on the other side. Now this u into u transpose v, I can write it as u transpose times v by u transpose u. This is a matrix.
In matrix, can we do that with matrices, bringing u to the other side?
Yeah, so we can do that. I'll tell you why we can do that, right? So now u is a vector, right? So u is in RD. So basically so think of this as a d cross 1 vector. U transpose is a 1 cross d vector, right? So v is a d cross 1 vector. So u transpose v by u transpose u into u. D cross 1 cross d into d cross 1, which is 1 cross 1 a number. 1 cross D into D cross 1 cross 1 a number, 1 cross D, D cross 1, which is a vector. Now I'm saying U transpose into V, right? So this is how it was. Now this is D cross 1, this is 1 cross D, this is D cross 1, right? So this whole thing is a D cross D matrix multiplied by D cross 1 vector, which will give me a D cross 1 vector, which is what I initially had as well, right? So that is possible, right? So I can write this as U transpose by U transpose U into V. That's okay, right? So, so basically what we have done is we have created a matrix, right? This matrix is called the projection matrix, at least in one dimension. It's easy to derive. We derived this. I mean, higher dimension is also easy to derive. Perhaps I won't do this in the interest of time today. But all we are saying is that this projection matrix has the property that if you input any vector to it, it will output the vector which is closest to this vector to the span of the matrix of the vector U, right? So that is what this matrix does, right? So now you can ask the same question about, is there a question? Yeah, sorry, is there a question? Srinivas, yes.
Sir, matrix multiplication is not commutative, right?
Matrix multiplication is not commutative. I did not do matrix multiplication here, remember? So I'm just, so basically this is a number, right? So this is just a number. Matrix multiplication is not commutative. But then I can, if I'm switching the order for two matrices, then that is wrong. Here, this is a number and this is a vector, right? So,
sir, it is scalar multiplication. It is clear. It is scalar multiplication. It is clear now.
Yeah. So it's just a multiple of number and a vector. So it's still okay. Okay.
Hi, sir.
Yes. Yeah.
Like you said, the vector V is as input we are sending, and we are getting the projection matrix. Here we didn't mention anywhere like we are sending U also. How will we come?
This is not an arbitrary projection, right? So this is projection only for U, right? So this matrix is specific for U.
Okay.
So if I want a different projection onto a different line, then I will need a different matrix that will involve that U.
Okay. If I want a projection, I need V and U both, right? Without them.
No. So what V is the input, right? So to create the matrix, you don't need V, right? So on which line am I projecting is determined completely by U. And the matrix itself is completely determined by only the line on which I want to project. Now, if you give me an input, then I will give you the output as the product of this matrix and that vector. Right? So this is P. This only depends on U. Now, the input to this is V, and then output would be the closest point of the input to the direction of U. Does it make sense?
In our case, U and V both are inputs, right?
Well, because we wanted the projection in the direction of U, right? So for the problem, both are inputs, but then for the matrix, only V is in.
Okay.
Yeah.
You're writing V as a function of U. Multiplying some factor of U with your V to get the output you want.
Yeah. So basically, this is a matrix. All I'm saying is that here is a matrix which, when you apply to any vector, will give me a vector along U first. The second property of this will be that vector will be the closest vector to the input vector.
Okay. So question is, what is U here?
U is something that whatever you wish to be, right? So if you wish to project onto a different direction, then you take that direction as U. That's all.
Okay, we need to provide U for getting the matrix.
Correct. So you need to, so the projection cannot, you need to project onto something, right? So that something will determine what that matrix is. And you need to determine what that something is. In this case, that something is U.
Okay.
Yeah. So if you're interested in projecting in a different direction, then you will get a different matrix, obviously.
Oh,
right?
Okay.
Yeah.
Like it will, whatever we are giving V, it will generate a projection. After we can decide U, whatever we are giving, accordingly it will calculate. Is that correct?
Correct. Okay, so now here is a question for all of you, right? So
just before that, just I have just one question, sir.
yes,
Question means I understand this thing in this way. This projection, what so far is going on, it's more or like same the linear transformation, because in linear transformation there is a matrix and there is a vector. Now my matrix basis will tell me this vector will going where. Now here this matrix, the creation of this matrix is a very special type, because U and U transpose. So I am making this matrix in the along with the U and bringing that vector to my this plane. Is it something like that?
yes, this matrix is very special. It is tied to U. It is special because it has the property that no matter which vector V you give, you will get a vector along the line of U. First point. The second point is that it is not any vector along the line of U. It is the closest vector to V. Right. So it is special in that sense. That's what it's called, a projection matrix.
And do you have, sir, any kind of simulation for this making of this matrix? Because this is very special that in particularly any kind of linear transformation. So what is the column that will decide my two coordinate, that's basis, from the standard basis to that basis. Here that one another transpose. I am getting that, but not able to visualize in that way.
What are you trying to visualize? Basically, that.
Sir, if any linear transformation, there is a matrix that say 1, 2, 3, 4. So my 1, 0, 0, 1, this is the standard basis in 2 dimension. Now 1, 0, 0, 1, 2, 3, 4. This 1, 3 will be the basis vector where I want to go. My I vector is scaled by 1 and my j vector is scaled by 3. Accordingly, my vector gets shifted to that basis. And since the linear transformation property hold, I am able to recover the changed vector in that way. Now, for keeping this thing in mind, now I am seeing this projection matrix. What it is doing, this is creating a matrix which basically brings setting the U direction plane and multiplying any vector to that and taking me to there.
Okay, I'll try to explain the projection from whatever we have seen so far, right? So now that is the question that I wanted to ask, right? So so now you have seen the projection matrix, right? So now forget all the calculations, right? So if I give you a matrix and say that, hey, this is the matrix which projects along the line of U, right? So now what would be the column space of this matrix?
The column space of the matrix will be the span of whole that plane, that direction of U, that plane is, it will be the column has to be lies there. Otherwise, where I will go?
Yeah, so where else can it go, right? So no matter which vector you give, it has to find a vector along the direction of U. Right?
Yes. Yes.
So which means the column space of this matrix has to be the span of U.
Yes.
Right? So where is the null space of this matrix?
Which matrix are U?
The projection matrix along the direction of U.
Null space.
Now again, geometrically think, which are the vectors which will get mapped to 0? In other words, which are the vectors? Of course, 0 will get mapped to 0. So that's true for everybody.
Perpendicular to that vector.
Null space will lie, sir, in any one point in that line, any particular one point. So all the vector that I have, when I transfer this to this plane one, because since I'm the column space is also holding the 0. So null space means any vector which brings me to that particular point in the line will those vectors creating whatever that is the null space.
Okay, let me slightly put it differently, right? So what is the property of this matrix P, whatever be the input, it will find the closest point along the direction of U. Now, if some point gets mapped to 0, then 0 should be the closest point along the direction of U to this vector. So which vectors will have 0 as the closest point? That's the question we are asking. That's the null space, right? So let's say this is our U. This is the span. Now, if I take a vector here, of course, closest is here. If I take a vector here, of course, closest is here. Now, which vector will have closest point as this?
It is the
Zero vector.
Perpendicular passing
Zero
through.
vector is fine. That is true. Anything
Perpendicular to the
A
vector.
line perpendicular to
Perpendicular.
U passing through origin.
Excellent, right? So if I take a vector here, this vector, now if I ask which vector is closest to U, it has to be this vector, right?
Yes.
Right? So now this also helps me tell that, well, what is, let's say this is V. We know this is U transpose V by U transpose U into U. That's what we derive. Now this happens to be 0. Now U is not 0. U transpose U is the length of U, that's also not 0. But then if this has to be 0, the only way this can happen is if U transpose V is 0. Right? So which means any vector which is perpendicular will get projected to the origin. And that will satisfy U transpose V is 0.
Yes, correct. Now it's clear.
Okay. Does that make sense?
Yes, yes.
Okay. Span of vector which are perpendicular to you. Excellent. This is in 2 dimensions, right? So in higher dimension, if you have 3-dimensional space where you are asking for projection onto a single line, right? So you'll still get U transpose V by U transpose V into U, but then the set of vectors which will project to the origin will be a 2-dimensional plane which is perpendicular to the vector U, the line spanned by the vector U, right? So U transpose V, the set of vectors which will satisfy U transpose V equal to 0 will not just be a line, but then a plane in that case, if your projection is along a line, right? So which means if your projection is along, now you can ask the question, well, why should I project it only along a line? Maybe I have a plane, right? So maybe I have a plane in 3 dimensions, right? So my diagram might be lousy, but yeah. So maybe I have this plane in 3 dimensions. Now I have a different vector V, right? So now this plane itself, I cannot write this as a using just one vector, right? So I need at least 2 vectors to, explain this plane. I mean, there should be a basis for this plane, right? So to generate this vectors in the plane, let's call that U1 and U2, and the plane is just the all linear combination of U1 and U2. Now I can ask, well, which is the closest point to the subspace spanned by the vectors U1 and U2, which is just the plane in R3, right? So now that would be, this point here, right? So you again go through the same thing, but then, well, you will get a different matrix, which will depend on U1 and U2, right? I think if this is U, if my memory is correct, so if this is U, so then this would be U transpose U inverse U transpose. This would be the matrix that would do the projection. Is this correct? I mean, for people who have seen this from the notes, I might get the exact equation wrong, but something like this, right? Yeah, Srinivas.
So the entire point of a projection matrix is to bring any other vector to another vector, right?
Correct.
But although the math seem to be right that it is bringing it to the 0, but how is it bringing to 0? So, but the math is right, it is bringing it to 0. I'm not understanding that part. It should bring on to U, the U, right?
It should bring on to the line, any point on the line of U.
So since all our vectors have 0 included, so it 0 can also, the other vector can also bring to 0. That is what you're saying?
But then it has to be closest to 0, right? So the projection is not just bringing to the line of U. It also has to be closest on the line of U, right? So if instead of 0 for this point, if I had chosen this point, right? So this length is more than this length, right? So where will I put this point, right? So can I choose this? This is also more than this. This point is also a bad point, right? So this point has the shortest distance to the origin, right? So if it is perpendicular to this line. Does it make sense?
Yes, sir. No, yes, sir. Now it is clear. Now I understood. All vectors should have 0, right? So that is why it is
What do you
bringing to
mean
0.
all vectors should have 0? What does that mean?
Sir, all vectors should have 0 means in whenever we take linear algebra, your first statement was it should be from 0, right? We all take that way.
Yeah. So your set of possibilities include 0 also, right? So, but then for this point, I mean, I cannot choose 0 as the proxy, right? So which means that I will entirely miss this length, right? So whereas if I choose this, only this small piece I miss. If I choose this 0, I'll lose the whole vector, right? So that's longer. So I won't choose 0 for those. 0 is a possibility. It's available in the set. I'm not going to pick that as the closest point, right? So because there are other points which are closer than 0 to this point. On the other hand, if it is perpendicular, 0 is the closest point, is what I'm saying.
No, now it is clear.
To visualize this, I mean, can we look at this as two lines and you have a light and where the shadow falls? Is that a way to look at it? Because for the perpendicular line, it will follow in the same line itself.
Yes.
For the longer line, it is falling in the point that you are showing. So can we visualize it like that?
Yeah, so you can visualize it like that, right? So actually, this is, I mean, so basically you have a, let's say
a beam of light.
There is a torch in this direction, which is perpendicular to the line in which you want to project. Now, if you have a point here, you basically move this torch till it hits this point, right? And now this will hit this point, right? So that's, if you want to visualize it that way, that's also fine. Yeah.
Okay.
But then all it is doing is finding the closest point in the line.
Yeah, basically where the shadow falls on the second line. I mean, where the shadow of V falls on you.
Yes, yes.
Okay,
Yeah.
okay, got it.
So I'm okay going for some more time. I mean, if people are getting late, you can kind of log off, but then I'll probably go for some more time. Yeah, so, so the next point I wanted to ask is, this is a quick, nice, fun question, right? So if I take a vector and then let's say I apply the projection matrix twice, what would happen to that vector?
Nothing will change. The closest point will still remain the same.
Once it is projected, then it is nowhere to go. In the same line, it will stay.
Correct.
Closest point distance is still going to remain the same. How many times you project doesn't matter.
Correct. So that is another way to define characterize a projection matrix. A matrix P such that P square will be P, right? So because even if I do P multiple times, it's not going to have any more effect, right? So that's just something that I wanted to put it out there.
But mathematically, it will give the same output only. I mean,
let's see.
Logically, it will.
Yeah. Mathematics is just logic. It has to happen, right? So let's convince ourselves. So for this particular case, it was U transpose V by, so the matrix itself was U transpose by U transpose U, correct? So now I take some vector. Now let's say that vector is in the direction of U itself, right? So which means that it will be some constant times U. That's what it means, right? So this is the input. Now this is my P. Now the output would be, well, what is this? This is C. The C is just a constant. I'll bring that out. And then I'll write this as U into U transpose U divided by U transpose U. Cancels. This is CU, which was your input. Right? So if you do it twice, it will stay there only.
Okay.
But if it is thrice, it is again the projection, right?
You can do it how many ever times you want, right? As long as you get tired, it is going to be the same, right? So because basically once you hit the shadow of the shadow is the shadow itself, right? So there is nothing more. You have hit the ground. There is nothing more you can move from there. That's what it means. Okay, good. Now, okay, so why do we care about projections, right? So I'll kind of give a high-level view of why we care about projections. Now, this is where solving this set of linear equations becomes an important thing, right? So let's say I have because this is a data science course, right? So let me motivate this with some kind of a data science problem, which is let's say you have you capture the following information for 100 or 1,000 days, right? So maybe the temperature, pressure, I don't know, precipitation. I'm just making these things up, but some features you capture, and then you also measure the, the rainfall in centimeters. Let's say maybe it was 30 degrees, maybe I don't know, 100 to 200, maybe 180, some numbers like this, right? So this was day 1, this was day 100, and so on, right? So you have a whole data set that you have collected. Now you want to understand how is rainfall affected by these 3 variables whose information I have, right? So how can I say something about rainfall? Can I forecast the amount of rainfall if I know the temperature, pressure, and precipitation, right? So this is the question I want to ask. Now, if I hypothesize that there is a linear relationship between these variables which can explain rainfall, which means that every day there is some combination, weighted combination of temperature, pressure, and precipitation, which will give me the answer as to what the rainfall is. Then I want to find out what this combination is, right? So because in the future, if I only have temperature, pressure, and precipitation, now if I know the combination, I can use that to predict the rainfall, right? So let's say I want to do that. So which means that now, given that I have hypothesized this is a linear relationship, I can write this as a matrix, right? So I can write the whole data that I have as 30, 100, 200, whatever, 40, 30, 20, blah, 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 all the data as like days, number of days cross number of features, right? So that would be my matrix. And then there is a rainfall vector, which is the output that I have observed, right? So this is 100 centimeters, 125 centimeters, 30 centimeters, whatever number this is, right? So I have observed these numbers. Now I want a set of weights, right? So W1, W2 till W number of features I have, such that if I combine this, it should explain my rainfall. In other words, I want 30 times W1 plus 100 times W2 plus 200 times W3 equals rainfall 100, right? So, and similarly, I want 40 times W1 plus 20 times W2 plus 30 times W3 equals 120, and so on, right? So I want to explain my output by a linear combination of the input. Now, let's now come back to whatever we have seen here so far, right? So this is the matrix that I can call as A. This is the rainfall matrix, let's say I can call as B. Now, essentially, then what I want to do is I want to solve AX equals B. Now, when will AX equals B have a solution? We know that, well, if I give X as input, the matrix A is going to transform X to the output space. And the output will only be in the column space of A, right? So it has to be in the column space of A by definition. Now, which means you can solve AX equal to B only if B is in the column space of A. But nature does not work using column spaces and row spaces, right? So your rainfall, though, will depend on your temperature, pressure, precipitation, whatever, whatnot. It's not going to be exactly a linear combination of these, right? So there are always going to be factors, maybe the pollution, which you have not accounted for, which might affect how much rainfall you see, maybe the number of trees, so many other factors which you don't know, right? So, which means you may not be able to solve AX equal to B. Though you have collected thousands and thousands of data of both the features and the output, you don't have a way to solve AX equal to B simply because your B is not in the column space of A. Now, that means that you can either give up and say that, hey, this problem cannot be solved. I don't have a relationship that I can understand about the features that explains the output. Or you can say that, well, fine, I can't solve AX equal to B. Maybe there is no X that satisfies AX equal to B, but then I will do the best I can. What is the best I can? Well, I have some, let's say R3, some RD, and then A takes it to some RK. I'm just making these general now. I know that whenever I apply A, it need not be the entire RK. It will perhaps be only the subspace of RK, which is the column space of A. The problem is my B is not in the column space of A. That's the problem that I have now, right? So B is somewhere else. It's not in the column space of A. I still want to solve this problem in the best possible way. So now what will I do?
Project that B.
That's it, right? So I'll just project this B onto this. Now this is my best guess, right? So which means that whatever I'm thinking of this vector is because of things that I've either not accounted for or simply because of nature's, variability of nature, right? So basically what you then want to do is you want to find that point, that X, which, now this will have some X, right? So there will be some X which will map to this AX. Now I want to find that X, because this, by definition, once I project it onto the column space, there will be some X which will map to this. Let me find that X, right? So now that X is what your linear regression finds, right? So if you project P, take the vector B, and then if you take P, which is the projection matrix for the column space of your A, right? So then I project B onto the column space of A, I get AX. Now I get AX, right? So I need to get the X, which is what the weight that I want, right? So now you kind of do, map back and say which X comes to this, right? So for that, I think the whole thing, if you work it out, so then you want to map. So this is something like AX, right? So your projection of this is AX, and now you want to do which one will give me exactly X, right? So this is typically not invertible, so you cannot do like an inverse. So you do what is called as like a pseudo inverse, which is just saying, fancy way to say that, well, I know that multiple X will map to AX, right? So because it's not just X, I can take anybody from the null space here and then add to X, and I know that it will also map to AX. Now that means that there is a whole, set of affine plane of vectors which will map to AX. Now you want that solution for whatever statistical reasons. I mean, if you have taken a statistics course, you would know this, but if not, it's okay. So there is a way to find that vector among all vectors which map to AX, find that vector which has the smallest length, right? So
we are projecting B onto the plane.
Onto the column space of A.
That's a plane. So we get a vector.
Yeah.
And that's a specific vector.
This is a specific vector. This is PB, correct?
Yeah. So
now by the virtue of the fact that it is in the column space of A, there must be some X which maps to this.
But won't it be a specific point? Because you are projecting onto a particular.
This will be a single point. This will be a single point. Yes. But then what I'm saying is that you need not get a single vector X that maps to this single point. There might be multiple vectors here that map to the same point. Why? Because there is a null space which will go to 0. Now I can add that null space to X and it will still come to the PB, right? If X goes to PB, then X plus anybody in the null space will also go to PB, because the null space goes to 0. A kind of extinguishes the effect of the null space vector.
Okay, so you're saying that essentially there will be multiple vectors that pass through this point.
Yeah, X plus null space of A. If I apply A to this, I'll get AX plus A into null space of A. This is 0. So this is AX. This, I mean, by this is what I'm saying as PB, right? So this projection matrix times P.
So if the null space is 0, then there is only one solution.
If the null space is 0, there is only one solution. Yes.
Okay, got it.
Yeah. Otherwise, what linear least squares would do is that, well, pick the solution which has the least length, right? So that's for some statistical reasons, which I won't discuss now. But your pseudo inverse, if you've seen pseudo inverse as a matrix, that exactly does that, right? So it will do this mapping, but then because there are infinite vectors on the left hand side, if the null space is not 0, you have to make a choice, right? So you cannot say that the solution is infinite vectors. You have to commit to some number, some vector on the left hand side, and you will commit to a vector which has the least length, right? So again, that is statistically a good choice. So, and that is what this mapping that does this is what is called as a pseudo inverse mapping. It's not an inverse, but then it's a pseudo inverse. Okay, so that's a question. The projection anyway gives the least length. Okay, so there are two things here, right? So the projection gives least length of what? Projection gives you the best proxy for B. But then there are multiple vectors on the left-hand side which can go to the same PB, right? So, and then among these vectors, I want to pick the one that is the smallest length, right? So the projection only acts on the right-hand side. Now I want to map it to the left-hand side, but I don't have an inverse if my null space is not 0. So which means I need to commit to a vector here. So I will pick that vector among all vectors which map to the projection. I will pick the vector which has the least length, is what I'm saying.
Sir, in the linear regression, we also learn something called the error function when we are doing. So can you relate that error with what is happening here? In which part that get linked?
Yeah. So that's so. Okay. So that error function is exactly this length. So this basically what was your error function? Your error function was sum over I equals whatever you have n vectors. I don't know what notation you used. So W transpose xi minus yi square. Is this what was used?
Yes.
Okay. So now, so basically in our notation, what we are saying is that, let's say we want to solve AW equals y, right? Now A has the vector, so or rather XW equals y. Let me change it slightly, right? So X has the vectors x1, x2, ... xn, and then there is a W which I want to find, which is equal to y, but then it may not be equal to y. So I want to know, I want to find that best W which minimizes the error in this sense, which is exactly saying that, well, I will pick this y vector and then project it along the column space.
So in the rainfall example, this is the factor that we are missing, and their best guess is the projection. So the error is the part that we choose to ignore and give the best guess.
Because of that error, we are not able to solve the equation with Ax equal to B. Because I don't find any X which can leads me to take me to the column space of A. And that is the difference, that is the error function.
Exactly. Perfect. Okay. So
when you say closest point, when you, I mean, going back to the previous topic, sorry. So you said that PB is equal to Ax has multiple solutions. It's a whole space, and you pick the line with the smallest length.
Yeah.
So how do you find that? Do you do that the same minimization, differentiation?
Yeah. So you can do that. Yeah. So that's how you would, if you had to write a code to do that, you would do that. But then it is so commonly used that it is given a name, right? So it's what is called as the pseudo inverse of A. So basically, this is a matrix, right? So basically, if you have a, let's say a matrix A, which is invertible, right? So now I do X, right? So X becomes AX. If I have to come back, I need to do A inverse of AX, right? So this will give me X. Now with the matrix, so that operator, that matrix that does this, which maps, vector to where it came from, is the A inverse matrix. But unfortunately, if A is not invertible, this does not hold, right? So your X you can apply A and then you will get AX. But now if I only tell you AX, which is in our case the projection vector, and I ask which X it came from, right? So I don't have an A inverse to apply. So what I will do is this is so standard now that this matrix is called A pseudo inverse, which you will apply AX to. Now this will give me some X tilde, which is not X. Well, there is no single X now, right? Because you could have started with any X and got X.
It's
now,
the best guess.
Yeah. So this.
No, I'm asking this function, right? So you're saying pseudo inverse.
Yeah.
So it should be a function. I will give some 1, 2, 3 vector to it, and I should get some point, some X.
Yes.
So what is that function?
That function is minimize over X. Yeah. Okay. So minimize over X. Minimize over every vector in the null space of A. X plus, well, I will say this way, right? So minimize over all X such that AX equal to P, length of me write it carefully. So I want to find the set of all x. So given, so this is, so A, this is this, yeah. So this is argument, right? So this, if I give you a B, now you ask the set of all x that satisfies Ax equal to B, right? And then I find that x which has the least length. That's what is.
Okay, so differentiate with respect to x here in our case.
Huh?
Ax is not equal to B.
X equal to B, yes. So what's the question?
Again, you would differentiate, equate it to 0, solve for x.
So it's hard, right? So because there is a condition here.
Yeah.
So if you don't have any condition, you can differentiate equate to 0. This is a conditional optimization. So this needs a different way of solving this problem, right? So this
We
is
will
not
get such questions in our quiz.
No, you won't. No. This is something that it's a standard way to. This is a standard operator basically, right? So if there is only one x that satisfies Ax equal to B, then you will get the inverse. A pseudo inverse is just the inverse, right? So otherwise, it's going to give you the one with the least length. Yeah.
Okay, sure.
Least length implies closest to origin. Yes, so yeah.
So as you said, there is only one x. Is there any indication that I can get while I'm doing this key? This x is going to lead me.
What indication for what?
No. So when you are applying that to find x tilde, out of many, there will be one x tilde which can lead me this day. Means how do I find this x tilde? Means out of many.
That needs us. You have to solve a problem, optimization problem to get that, right? So that can be given by this pseudo inverse matrix is what I'm saying, right? So there is a functional form to that, which is what is called as the pseudo inverse matrix. I don't remember the exact functional form.
So one thing, why are you adding that argument? Because this is giving you x. So again, going for argument means I'm not getting that. For every x that falls on the column space A is equal to B, find the norm, find the minimum value of x for which the norm is minimum.
Yeah.
And what is why you are giving argument?
The argument is because if I don't give the argument, this is a number, right? So this is the minimum value. But then I want to map the vector B to a vector. That's why I'm giving an argument. Argument which means that the value of x which has the least length. I don't care about the length, right? So I mean, if I take the vector B, if I take the inverse, then I will get a vector, right? So on the other side. So what the output should be?
So basically, you are looking at the input vector, which is resulting in this value.
Correct. Yes. Exactly.
The input vector, which is resulting in this value.
That's what I need, right? So because that's what your
so
inverse.
after getting the input value, input vector, input feature vector, then how we are going to relate with the rain forecast now?
Yeah. So once you have that x, right? So now so what is this x? This is going to be in the feature dimension, right? So if you have 5 features, this is going to be in R5, or in our case, there were 3 features. This will be in R3, right? So maybe this is like 10, 20.3, 40.6, right? So this is what we got. What does this tell us? Now, if I give you a temperature, pressure, precipitation values, which is, let's say 40, 60, 20. Now, if I ask you for the rainfall, now you can simply do 40 into 10 plus 60 into 20.3 plus 20 into 40 point using these numbers. And that would be your prediction. Right? So that is what. Yeah.
So basically you're finding the x tilde, this argument.
Yeah.
And then
so that argument gives me the weights for each of the features.
Okay. You are getting the weights, not weights. Okay.
So I think there may be notational difference between what
yes. Got it.
Get confused with.
Okay. Basically, argument means the value which the vector which gives the minimum value. That's
exactly.
What argument means.
That's what argument means. Yes.
Okay. Thanks.
So didn't we assume that Ax is not equal to B?
No. Here we are as okay. So here I'm saying that I will first do the projection. The projection will satisfy, there will be at least one x such that Ax equal to the projection. Yeah. And for that projection, I will apply this.
Okay.
Ax is not equal to b. I agree, right? So so if that is the confusion, again notational confusion, let me say this way: Ax equals the projection. Does it make sense?
Yes, sir.
Yeah. Good. So hopefully that was slightly clearer.
Yes, sir. So there was one place in the lectures where they mapped the squared. They found the squared error and then put it onto the projection. Why do they do that?
Say that again. They find what?
The squared error, and then take that vector and put it onto a projection, and then find the difference between PB and the B.
I don't completely get what you're saying. So yeah, so that's what you're trying to minimize, right? So given A, P is determined. P is a function of just A, because you want to project onto the column space of A. That is completely determined by A. And now your rainfall values are B, right? This is actual rainfall values that you have, right? So this is rainfall values observed, right? So now what am I saying? So yeah, so you want to. So how do you want to explain this rainfall values? You want to explain this as AX, basically, right? So that's basically what you want to do. So all you want to do is you want to find that X that minimizes AX minus B, right? So the length of AX minus B. Right? So I'm saying that's equivalent to saying that doing this projection. That's all I'm saying. Is that what you're asking?
Yes, sir. So there was one example where they took A theta equal to B, and then they found the vector that solves this the theta and theta dash. I mean, they wrote it in the form of theta x plus theta dash, and then solved for theta and theta dash using the row transformation. Then what they did was they did the least square for this. I mean, they basically found theta and theta dash, and then after that they projected this onto a plane. Why are they doing that?
No, but how will you find the theta and theta dash? By doing what?
They did a row transformation first, and then they did the least square. A transpose A theta cap is equal to A transpose B.
Yeah, least squares is doing the projection, right? So least squares means you're projecting.
Yeah, so you get a theta and dash and theta. Next step, what Sir did was, the best line they could get was some, let's say, 5x plus 6 or something like that. They got a line, they got an equation of form theta x plus theta dash. And then in the projections, they substituted it. So they have a vector, projection vector, and they got this, they substituted those values in this line equation, as in the 5x plus 6 or whatever equation is it. And they got P1, P2, P3.
Okay, I am unable to kind of get the question.
I can ping.
Maybe, yeah. So maybe we can ask.
The slide has that. So I sent the slide.
Okay, so I'm going to come back to that. Okay, so that people have other questions.
She can post on discourse, and I'll forward the question to you, sir.
Okay, thanks.
Okay.
I'll do that. Okay, so quickly, are there any other questions? I know I've taken way more time than needed, but if there are other questions that I need to answer or any clarifications. Okay, things are okay. I mean, I hope session was useful. So I'll take a look at that and maybe I'll answer that separately, because I think there are some notational, differences. I mean, I'm just using my notation. I did not I should have gone through the notation, but I did not. But yeah. Okay, so any other questions? If not, we'll perhaps close for the day.
No, sir, just one part out of this whole discussion, where this eigenvalue and eigenvectors comes into the picture. So far, whatever we have done, because just one question in the practice assignment, I'm not very clear what is happening there. I'm just read out that question. It is say that P is a projection matrix. And then they said that the eigenvalue corresponding to every non-zero vector lying in the column space of P is 1. If you can just explain this part.
Okay, this is so we already have seen the answer to this, right? So it's just a matter of reflecting. So you have some P, which is a projection, right? So you have V, and then you project it onto some column space. Now this is PV, right? Now, if you take any vector in the column space itself, right? So let's say I take some other U, right? So what will happen if I do PU? So this is already in the column space where I want to project. So if I do P times U, what would happen?
It is just give me the vector in which is again lying in the same column space.
So
and also it is
we will get you.
Yeah, so if you take a vector which is not in the column space where you are projecting, you will get P times V, which is in the column space, which is closest. If I take a vector in the column space itself, which is the closest vector in the column space to a vector in the column space itself? It's itself, right? So,
yeah.
So this is PU is U. So now what does this equation remind you of? So let me write it as PU equals 1 times U.
Okay.
Now if you try to connect it to the question itself, I think you should be able to see that, by definition of an eigenvector, eigenvector's definition is AU equals lambda U. Now here is a P, here is a vector I input, it just scales, doesn't even get scaled, right? So it just stays if it is in the column space, which means any vector in the column space is an eigenvector with eigenvalue 1 for the projection matrix. Now, any vector in the null space is going to get projected to the, of course, to the 0 vector. That will have eigenvalue 0, right? So these are the only eigenvalues that a projection matrix can have, 1 and 0.
Okay.
And it will have how many vectors with eigenvalue 1? Well, that will equal to the dimension of the column space itself, because you have so many, free variables there. So you can only make so many independent vectors there. Does it make sense?
Yep. Yeah.
Okay. More questions? I was hoping for the explanation of multivariable calculus. Okay. Maybe next time we can try that. Intuition behind dot product. Okay. So I thought we did an elaborate thing. Dot product is just the projection, right? So your intuition for dot product should come from projection. If I take, let's take 2 vectors, and then I ask what is the dot product, U and V. Now you can say that if I project U onto V, right? So how much should I scale V to get the projection? That is your dot product. Now, whenever, let's fix this. Okay, maybe this is V, this is U. Now, whenever I take a vector, in these regions, if I project, I will, so this is my U, right? So I will get a positive scaling, right? So maybe here will go here, this vector will go here. It's all on the positive scale. If I take a vector in the perpendicular to the original U, we already saw that it will get projected to the origin, so the dot product will be 0. Whereas if I take a vector which is on the other side, right? So let's say if this is V, it will get projected here, but because U is pointing on this side, now I have to flip U to get to this part, right? So which means that there is a negative scaling involved. So these dot products will be negative. So essentially what we are saying is that if I fix a U, now I can ask where are the set of all vectors which make a positive dot product with U. Now that would be this set. And where are the set of all vectors which make a negative dot product with U? That would be this set. And now where are the set of vectors which make a 0 dot product? That would exactly be the perpendicular set. Okay, so the dot product can be thought of as, I project my vector, one vector on the other, and then ask how much should I scale the U vector to get to the projection. If I have to scale in the negative, then it is making a negative dot product. If I have to scale in the positive, it's making a positive dot product. If it's exactly perpendicular, it will make a 0 dot product. That's the intuition. Does that clarify?
Yes, sir.
Okay, good. Okay, so I think in the interest of time, we'll close here, perhaps. Yeah, Satyadeep, yes.
Yeah, sir, it is fine, but just wanted to request, if possible, maybe sometime in the future, if we can hold another session for multivariate calculus.
We'll try that. Yes, yes. So one of us will hold the session, right? So I think all the faculty involved in the course will have these sessions. I will anyway come back and have a session when you guys go over the topics that I have covered later in the course. But yeah, so I mean, either I'll come or somebody.
Okay, sir.
Optimization
It
problem.
has been great for today's session, sir. Thank you for taking this.
Thank you.
Thank you, sir. It was
Thank
really
you,
helpful.
Thank you, sir, for such an insightful.
And all the best for the quiz.
Thank
Thank
you very
you.
much.
Thank you, sir.
Thank you, sir.
Bye.
Thank you, sir.
Thank you, sir.